always vital in the part of learning of chemistry. Dear students, you all know that although online materials are available for plus 2 stage, but very few materials are there for degree honors students. So we had selected certain topics like being chemistry, which should be delivered by Dr. Diganta Sharma, Associate Professor and Head of the Department, Dibrugarh University, Chemistry. Then we have selected another topic which is also vital, that is quantum chemistry by Dr. Rahul Kaur, Assistant Professor and Department of Chemistry. And another topic which is also very important is thermodynamics by Dr. Anupal Borua. He is also from Dibrugarh University. And another faculty is there. Another faculty is there with us. He is Dr. Ankur Kanti Guha from Cotton University. He will discuss today about organometallic chemistry. So, dear students, we are trying to give you a platform so that you can have some better idea about these topics, which will be always necessary for you while studying chemistry further. And as the coordinator have already informed you that you have to post any query that you want to know from the resource person, that will have to be posted on Google Meet within 45 minutes. And we will select certain vital questions among them and will put forward to the resource person for discussion. So one more thing, before we are going such a situation, we need to be patient, as our universities have not given any guideline regarding examinations. But I hope that all of you will be remain patient and be alert to yourself as well as to your family and society. As a student of science, you should have you should aware your society, should respect the COVID warriors like doctors, nurses, and police personnel also, and also should keep a close eye on your society, that those people who are in quarantine should follow the SOPs that is being issued by the government as well as Ministry of Home Affairs. I wish you all the best and have a patient hearing of this webinar. Next, I would like to request Ms. Neharani Kumar, Assistant Professor of Department of Chemistry, Dhemaji College, to drive the rest of the proceedings. Thank you once again. Thanks.
Hello, am I audible?
Yeah.
Thank you. Thank you, sir, for your speech, for introducing the webinar on interdisciplinary topics in chemistry for the budding chemist. So now I would like to invite our Honorable Principal, Sir, Dr. Deepak Kumar Niyog, to give the inauguration speech of this webinar. Sir, please.
Yes. Am I visible?
Yes, sir.
Okay. So welcome. Good morning, everybody. Actually, at this stage of this under COVID-19, entire world is facing problem, particularly in health sector. Specifically, the health workers as well as health department, all are doing their best to face the problem. Yeah. Yes. I'd like to request everyone to not presenting and also coordinator to control as far as possible. So at the beginning, I like to welcome all participants, particularly the student community, not only from Assam, from entire nation. Means what I have seen, the participants from outside states are also joining here, and as far as available information, I think more than 15 participants have joined in this webinar. And though I have not seen in the screen, I think our expert has already joined in our meeting webinar. And as HOD has informed, I welcome Dr. Diganta Sharma, HOD Department of Chemistry, Dibrugarh University, Dr. Anupul Barua from Department of Chemistry, Dibrugarh University, Dr. Rahul Kaur, Department of Chemistry, Dibrugarh University, Dr. Ankul Kanti Guha, Department of Chemistry, Cotton University. So, welcome everybody, and I'd like to give a small introduction of Dhemaji College. And we are in the northeast part of Assam, and being a oldest institution, premier institution of the region, it was established in 1965, and here from the day of starting the institution, spreading successfully higher education, not only the entire district as well as for the entire nation. And we feel it's our responsibility to upgrade our education-friendly environment as well as to introduce the high-tech facility to the students. Now, like chemistry subject, it is very difficult to continue academic activities without touching, without presenting a teacher. But because of this situation, we have to take the advantage of technology, and as well as we have to think how to use for the betterment of the students using this technology. Definitely, attending online classes for 5 6 hours daily in front of a small screen, it is very difficult, as well as to teach like chemistry subject, which need more practical as well as more guidance of teachers. But yeah, someone is presenting. Then I request not to present Sagun Paliwal, please. Use the Saturn, not the present. Neha, please. Anyway, am I audible?
Yes, sir, you are audible.
Yeah. So means in the midtime, someone trying to present. So anyway, so the chemistry department of Dhemaji College, they have take up this webinar to reach the students, even though it is a difficult subject, but for this webinar, they're trying to reach the students and to cope up the present situations. And I hope the experts will deliver our students, community, as well as all participants in a better way to understand the chemistry as well as to understand the situation. And thing is that we have to cope up with that situation. We must have to go forward. We have to come forward, not go forward, come forward to cope up the situation. So I welcome everybody and I formally inaugurate this webinar, and with this word I say it is inaugurated. And I'd like to lastly I'd like to thank Dr. Manas Morpuzari, Naharani Kumar, taking this risk of coordinating such a webinar from a remote area where the network is a very big problem, as well as HOD Dipin Kakuti taking initiation to hold a webinar, communicating all these experts, as well as Manaspati Borwa taking part in this preparation. And I hope this webinar will be a successful one. Thank you. And this is the hack one. We continue.
Thank you, sir, for your wonderful speech, and thank you for your moral support to organize this webinar. So I would now request participants to please stop.
The mic is not audible. It's not audible. Yes, if some technical difficulties with NEHAP.
Hello, am I audible? Hello. Okay. So I would like to thank our honorable principal sir, Dr. Deepak Kumar Niyok, for inaugurating the webinar and giving such a encouraging speech to our participants, and also providing a brief introduction about the speakers. So I have a request for the participants. Please do not present anything on the screen. Please keep yourself mute and attend the seminar given by the speakers. And if you have any questions, as told earlier, please post your questions in the comment section, and we will pass on the questions to the respected speakers. Okay, so now we have our first speaker in line, that is Dr. Diganto Sharma from Dibrugarh University. So, Sir Diganto Sharma is currently an associate professor and head of Department of Chemistry at Dibrugarh. So let me briefly introduce him to you. So Professor Diganta Sharma did his master's from Guwahati University. Then he moved for his PhD to Pune and he completed his PhD from National Chemical Laboratory. He also did 2 postdocs, one at Japan and the other at United States of America. And now he is a brilliant academician guiding several PhD students, and his current area of work is green chemistry and catalysis. So with this brief introduction, I would like to welcome Diganta Sharma sir to present his talk to our students. Thank you.
Am I audible?
Yes, sir.
Okay, thank you, Neha Kumari, for this such a nice introduction. First of all, I'm very much thankful to the principal, Dr. Deepak Kumar Neo, HOD, Dr. Dipen Kakoti, and the organizers, Dr. Manas Propin Borpuzari and Dr. Neha Kumar, for organizing this event at this pandemic situation. I like and I appreciate it really. So I'm listening. You are listening to me, right?
Yes, sir.
Okay. So today I'm going to talk about green chemistry, but before that, I should share the slides, I guess. So
Yes, sir.
Yes. So can you see the slides?
No, sir, not yet. Yes, sir, now it's visible.
It's visible, right? It is visible
Yes,
now?
sir. Yes, sir, yes.
It's okay.
Yeah.
Okay? Yeah, okay. So,
Yes, sir.
So I will talk about mainly the recent advances in environmentally benign synthesis. The reason that I choose to talk about green chemistry is that nowadays, we chemists are, to some extent, we are the most responsible person creating environmental pollution everywhere. So rather than anyone else, we chemists are the most responsible person. So what I thought that I would highlight today certain things on green chemistry which are usually not available in a normal green chemistry book. In fact, I wrote a book on green chemistry. Can you see it here? This book I'm showing you because I don't see anyone. I'm just looking at my slides. Can you see this book?
Yes, sir.
Yeah, okay. So this is a green chemistry book with
Yes, sir.
along with me, Dr. Biswajit Choikia from Digboud College is another author. So if anyone is from Digboud, then they'll know it. So we prepared this book for our undergraduate students of all Indian universities. So most of the things are included in this book. It was published by Koilani Publication. So I will mainly highlight today or discuss certain things which are not included in general green chemistry books. So first of all, because I prepared this talk only for undergraduate students, so I'll address from now onwards, I'll address only the students. Okay, so dear students, now by definition wise, if you just most green chemistry is not like it's a how to say simple reaction or it's a special branch of chemistry. It is if you look at the most widely accepted definition, it is the utilization of a set of principles that reduce or eliminates the use or generation of hazardous substances in the design, manufacture, and application of chemical products. That means it is about green chemistry is about reducing waste materials, hazards, risk, energy, environmental impact. So my second slide is now visible. I'm in the slide number 2. It is scrolling
No,
up
sir,
or
it's
not?
still at first slide.
So then how to do it? Every slide I have
It's
to present?
yeah. Now it's visible, sir.
Okay, so it takes some time, that means. Okay.
Yeah.
Okay. So, yeah, as I explained you, it is all about just a practice that reduces.
Excuse me, sir.
Yes. Yes.
Excuse me, sir. Can you
Yes.
please make it slideshow? It's not in Zoom version.
I am in my laptop, it is in slideshow actually. So I don't know how to do it here. Wait a minute. Or did I make mistake? How to do it? Can you just guide me?
Actually, sir, the entire PowerPoint screen is visible.
So you are not seeing the slideshow, right?
So you can move completely to the PowerPoint and be away from this Google Meet screen.
Okay, that's what I'm doing. Okay, I'll not go back to the Google Meet screen. So I am now in the PowerPoint presentation slide mode view. Okay. So is it okay now?
Actually, sir, your complete PowerPoint screen is visible, not only the slide.
Like if I go back to the first slide, is it okay now? No? No?
No, sir, still it's in PowerPoint mode only.
Not in like zoom out, right? Okay, then how to do it? I don't know. I am now
So you
opening the.
can, so
Yes?
you can zoom the percent. You can zoom the percentage. It's 50%, right? You can make it some 70 or like this in the PowerPoint. This zoom option.
Yeah, that's what I did. It is in like 100% in my laptop at least. But I can see some option type of the window is being shared. Click to control sharing. We'll to control now. Maybe, but how to do it? Wait a minute, I can call my friend. Wait a minute. Or while sharing at that time, control, can you come down and help me? Okay, my colleague Anup, I called Anup, who has a talk after me, so he's coming downstairs to help me out here. Just wait, okay?
Yes, sir.
Because or there's another way, because there are two options in the you are presenting option. One is like file, one is window. So I did the window. I did the windows. So I can do one thing. First, see if you can do. Otherwise, what I'll do, I'll stop this presenting and then I will share the file. I think that will work. Because this is my first webinar. I'm
No,
sorry.
no, sir, it's okay. Yeah, that's not an issue.
Yeah. So yes.
So I request the participants to please bear with us because since this is a webinar, so there can be some network issues. Please pardon us for that.
Exactly, yeah. See, this is the outlook. You are presenting, so shall I stop it? Stop. Okay, we'll stop it for a while, the presentation, and then we'll reboot it. Okay, so stop this. Okay, I needed a window. Come down. This one, Microsoft PowerPoint Green Industry. Allow. And then this. Oh, maybe 100% hit it, right? Let's see. So it is better now. It is okay now, no? Hello? Hello? Is okay now? So now if you go back to the earlier slide, like in chemistry definition, now you can see in full mode, 100%. Hello?
Hello, yes,
Hello?
sir.
Now it is okay?
Hello?
Hello?
No, sir, still it's in PowerPoint mode. Hello?
Yeah. Still in PowerPoint?
Yes, sir.
Still in PowerPoint?
Means the complete screen is visible, not only the slide.
Yeah. What to do? Still, right? Then what
So
to
your
do?
screen is not visible.
Yeah, it is not visible now. Wait a minute, wait a minute.
No, sir, your power.
Okay, present now, a window. Then in chemistry. Hello. It is okay now?
Sir, still your entire PowerPoint is visible.
So there is another option. It is called, instead of how to say, I'll try last one, okay? Otherwise I'll speak like this, okay? Wait a minute.
Okay, sir. Okay, you can continue then.
Present now, interest. Target to PowerPoint, interest. Interest. Allow. Now can you see it okay?
Yes, sir. Yes, sir. Now it's proper.
Okay, if I go back now, can you see it full screen?
Yes, sir. Yes, sir.
Okay. Fine, I see. I think we should share entire screen. Okay. So am I audible?
Yes, sir.
Hello?
Yes, sir. You are audible.
Okay. Okay, sorry for the interruption. Anyway, okay, so we are talking about reducing waste material hazard and all these things. Okay, now before we start a real green chemistry, now what did, hello?
So your presentation is not visible. Now I can see you.
Oh God. Okay. Oh, wait a minute. Last bit. Entire screen. Microsoft PowerPoint. Chemistry allow. Come. There's a little problem actually. Yeah. So now you can see no.
Yeah, I can see, but this time it is complete PowerPoint.
Yeah. So you can see the complete PowerPoint, right? Hello.
Yeah, not only the slide. Yeah, yes, sir. I can see the complete PowerPoint.
That is okay.
So can you make it slideshow as you had shown just few minutes before?
And now what is this? What is coming? Nothing.
So this is the PowerPoint screen is also visible.
But there is no contents, right? Green chemistry is about reducing and all these things. No.
No, it's some waste slide. Waste word is visible.
Oh, okay. That's the one.
Probably the fourth slide.
Let me talk to Manoj Babjay. He's on the phone. Just a moment. Hello. Slideshow to click here, so then Rahul Jam. Okay, Dr. Rahul Kaur is here. Let me see what we can do. It's okay. Problem is
Okay, sir.
presenting. Then stop presenting. Okay. Then
present now.
okay.
To present अपने window.
It
Window
is a
हाँ,
file
अपने window
window.
window. हाँ, select window or screen. It
No,
will
no,
window. Presentation नाम तो क्या?
Within chemistry has some Microsoft PowerPoint in chemistry. I can help there.
Imagine करो नहीं.
Just answer the question. No, hey, do a second. No, one second to have GTA here.
It
A second file do.
it is how.
Head is selected as a zero.
It is
Allow.
it. The window is being shared to control the sharing.
It is
It is a guy.
now is it okay?
Tomorrow how much? Internet की university
Now is it okay?
Sir, it's not still visible.
No, not now.
There are two No, there are two presentations I can see, green chemistry old and green
Yes,
chemistry.
yes. But then we select the green chemistry and we can do. How to do it? You are just in question. Just property green chemistry. That's it. এতিয়া কইলে এখন স্লাইড এখন আহিব তো কিছু এখন আহিব that time দিয়ে এটা করছি
itu plan को internet slow है. Heavy internet slow होने time.
মানুষের চাইছে না
No.
Is it okay now? Okay.
No, sir, entire PowerPoint is visible.
Sir, press the button on slideshow.
Slideshow in PowerPoint presentation, right?
So please hit the F5 button and then the slideshow will appear.
We have checked that anyway, we have to click the slideshow button, right? Instead of that F5, same thing, right? Everything? That is okay?
No, sir, entire PowerPoint is visible, still the same.
Laptop को change कर सकते. Laptop को change कर सकते.
No, like that.
Sir, press the F5 key.
Yeah, that's what we are doing.
So it's
Excuse me, sir,
visible
press
this
the
way. You can.
F5 key.
Oh, so this way it is visible, right?
Yes, sir, it's visible. You can continue.
Yes, sir.
So yeah, rather than spending time on this one, let me continue this way, okay?
Okay, sir.
Okay, so can you see now the slides?
Excuse me, sir, press the
Yeah,
F5
yeah.
key.
Yes, sir. Participants, please mute yourself. Participants, please mute yourself.
No, but when I put F5, then I can see the slideshow, but you don't see it, right?
Yes. Sir, okay, you can continue. Sorry, it's visible to everyone. So you can continue in this way.
Now it is visible?
Yeah, means the things are clear, so you can continue it in this mode itself.
So now can you read? What is the title of this slide? Can you read?
Yeah, it's waste during the past 35 years.
Oh, that slide is still there. Okay, now I am in the next slide. Can you see where does waste come from?
No, sir, not yet.
Or if I put escape button, now can you see the next
Yeah,
slide?
now it's visible. Where does the waste come from?
Okay, wait a minute, one more time. Then now I'm in the next slide. Where does waste go? Can you see?
Yeah, some pictures. Yeah.
Pictures. Yeah, then now the 3 hours of the environment you can see.
Yes, sir.
Okay, I'll go this way. Okay, just leave it. Okay,
Okay,
because
sir.
already a lot of time. Okay,
sir.
sorry. Okay, get back to work now. Okay, so I was just talking about that waste generated, that or we are generating the waste every year. Number is used. This is an old slide, but just to get the essence, I'm just showing you. So whatever you use, we know it, right? We use all packaging materials and plastics, everything. We are so much dependent on plastics. Like we make, as you can see, but slide is not coming anyway. Like plastic cans, plastic bags, everything. More than 95% things we are mostly dependent on plastics. Now, if we make a list that when we make something, when we transport something, when we use something, and when we misuse something. So after using the things, we just throw it out. And where do they go? So you are following me, right?
Yes, sir.
Okay. So these waste go, like municipality cars, they usually come to everyone's home, particularly in the town area. So they pick up from home everyone's, then like they dump it in a particular area in a town. But after that, there is no treatment, as far we know. So then the result. They eventually go, mix with landfills. They go to water. They contaminate the water bodies, and they contaminate our environment. So that means we should be careful. So in that, similarly, reuse. Like if you can, instead of throwing something, if you can reuse for some other purposes, that will somehow save the environment. Similarly, if the best way is to recycle, there are 3 kinds of recycling, like primary recycling, secondary recycling, and tertiary recycling. What primary recycling is, like when you use an item without changing anything. Suppose you have a table or chair, and suppose you don't need it and someone else is using it. So in that case, you can say that is primary recycling. Secondary recycling is like you have a newspaper, or you have suppose glass bottles or plastic cans. Instead of throwing it, you can cut it in a certain place. Like nowadays, you can see like some people, they do all the waste bottles for plantation, or suppose for newspaper, you can make some how to say for anything that you can make. So these these principles are very important, that we follow these 3 R's. Particularly, as Nahak has said, that I have experience living in the United States and Japan for 5 years. So there you can see there is a website called Craigslist.com. I've been in India also, but it is not that popular. But in many other countries, Craigslist is very popular. So what they do, everything, if you don't need it, suppose you have a table or chair you were using, but now you got the money, or you don't want to use it anymore. What you can do is just put it in Craigslist.com. Someone else who cannot afford to buy a new one, they can use it. So this way, at least you can help others. Similarly, nowadays, OLX.in in India, it has become very popular. Now, I'll tell you what are the human causes. Some, how to say, natural disasters. We call it as earth-altering accidents that happened in the past due to the negligence of our, I can say, the chemists. Here's a list. Can you see the list? There are many,
Yes,
like
sir.
Love Canal to the Texas fertilizer plant. So I'll explain only 1 or 2, because if you want to know more about these incidents, you can go through this book. So Love Canal is a place in the United States, like earlier, maybe around in 1930 or 1920s. All chemical companies they were legalized to dump their or throw their waste material to that place. Then they continued for at least 20 years, and then they stopped it. Then around 1950, the United States government they allowed some migrant immigrants to start live. I mean, they shifted certain group of people to that place, and they started living there without being told that this place was used for chemical dumping. Now, as a result, what happened after 4 or 5 years of living in that place, people started developing a lot of dangerous diseases like cancer, liver diseases, etc. They started feeling a very bad smell coming out of those areas. Then trees, the shades of their leaves, and all these bad things happened. And later, it was figured out that it was due to the, I mean, chemical waste deposition in that place. And finally, then those group of people, they were like withdrawn, I mean, shifted to another place. And after 40 years of treatment, in 1990, again, the place became I mean, livable. How to say, the people started living in the place. So these are some of the incidents. I mean, a lot of people died. They had to sacrifice their lives just because of our negligence. Similarly, we know very well about the Bhopal chemical leak tragedy in 1984. Because Union Carbide industry, they used the methyl isocyanate for synthesizing a pesticide, and so the leakage of methyl isocyanate caused the death of around 3,000 people, and around 10,000 other got affected. So these are some of the examples. Now, even like recently in Bagzan, those who are from Assam didn't know that what the tragedy is going on in Bagzan area, that it is all again the negligence of people. I mean, somehow chemistry is associated. Petroleum means all chemistry. So now I'll tell you, because we're talking about green chemistry, now we should know about how this concept was evolved. Because earlier there was no term called green chemistry, but first time in 1990 this term was introduced. Now, how this term came to the scientific area? We have to go back to 1961. It's a drug called thalidomide. Can you see this drug molecule? Okay.
Yes, sir.
Yeah, it is visible, right? Okay.
Yes, sir.
So this drug molecule has a chiral center,
Yes, sir.
asymmetric carbon center, as you can see. Now, this drug was first prescribed in Germany to the pregnant women, because pregnant women who were going to work, because in Germany at that time there were a lot of women workers. I mean, they used to go for work all day, then they come back. Now, during pregnancy, this is a general tendency that women, when they get sick and they don't feel like fresh. So this medicine was prescribed, or they were used by pregnant women to feel there are a lot of background noises coming on. Anyway, so okay, so then what happened? The women were very happy because they were able to work freely, even if they were pregnant after taking this medicine. What happened? What happened? That after using this medicine for some time, after a few years, they observed that there were a lot of babies who were born. I mean, how to say? They had a lot of birth defects, like they did not have, suppose, a number of fingers, they had problems, or there were many problems with the babies born out of this pregnant woman. So even in Germany alone, 10,000 babies were born like this, and they were, that's why, termed as thalidomide babies. And like 5,000 in Germany alone, and then in the rest of the world, 5,000. So then immediately this drug was withdrawn from the market. So this is an incident in 1961. Then at the same time, in 1962, Russell Carson, an American marine biologist, she wrote a book called Silent Spring. She discussed about the effect of certain pesticides, for example, DDT, the use of DDT and other pesticides, how they could spread throughout the food chain and cause irreparable and unanticipated harm to the human being. So as you can, you should always remember, those who are interested, I mean, those who study green chemistry, they should know these two incidents very well. First one is thalidomide, and second one is silent spring. That means spring becomes silent. So it's a very catchy name. Then some environmental disasters, as I explained in the previous slide. And so it took almost 30 years, that starting from thalidomide to all these environmental disasters, there were a lot of meetings going on. And finally, in 1990, the Pollution Prevention Act, called PPA, was passed by the United States Congress. And in that meeting, until that, there were no formal meeting on how to control pollution prevention. So in that meeting, there were a lot of different ways had been developed to deal with pollution prevention. And one of the ways was green chemistry. So now I'm in this phase where I'm discussing 12 principles of green chemistry. Can you follow me? Can anyone tell me whether you are following or not?
Yes, sir.
Oh, okay.
Yes, sir.
Because otherwise I'm not sure whether anyone is following me or not. Okay. So
Yes, sir.
so then Paul Anastas and John Warner from Environmental Protection Agency and American Chemical Society, they developed or they suggested 12 principles that, I mean, if we follow those 12 principles, then when we design a synthesis, that can be considered as green. So what are these 12 principles? I'm not going to explain in detail, but as the principle says, that first one is design chemical synthesis to prevent waste. Because when we design something, suppose if we are doing a chemical synthesis starting from A to product B, there is always a possibility of formation of unwanted product C. So that is the waste material. So we should always try to avoid those waste material. Then design safer chemicals. It is obvious we should not use. And the third one is almost identical, that we should not use hazardous chemicals. Then, of course, use of renewable feedstock is another important issue, because this is a very vital issue, because now whatever we are using, starting from the morning, the toothbrush to the end, I mean mobile, everything, our clothes we are using, they all come from the petroleum products. So, but they are non-renewable sources of energy. So it is high time that even it has started already, people started working on the renewable feedstock, but cost associated with the renewable feedstock is quite high, so still we are dependent on petroleum feedstock. But at some point, maybe 100 or 200 years later, we will have to be dependent on those renewable feedstock. Similarly, use of catalysts, no stoichiometric reagents. Stoichiometric means 1:1 ratio of reagents. Definitely it is not used because that will be very costly, and if you use the catalytic amount of reagent, that is always most welcome. Similarly, then then another important point is maximum atomic economy and use safer solvent. These are the 2 points that I am going to discuss today in detail, and which are not included in these books or in any green chemistry books in detail. So I'm going to discuss those 2 points mainly. Then increase energy efficiency. Yes, so now as an alternative approach, now those reactions which do not proceed at room temperature, they are usually carried out in plants like microwave energy or like in plants of ultrasonication. So microwave and ultrasonication are considered as a greener techniques for chemistry. Similarly, then minimize potential. So these are some other related principles. So now, as I said, I discussed these 2 points, that is maximum atomic economy and use safer solvents. Now I will take you to the atomic economy part. Now, what is called an atomic economy? But before that, we should understand the percentage yield, like, because we chemists are more concerned about percentage yield. Not we do not consider how much byproducts are formed or like how much time it takes to purify products. So we're not concerned about that. We are more concerned about if we are expecting a product B from product A, then how much percentage of product B we got. That is the only thing we take care. So that's why percentage yield says that actual yield of the desired product divided by theoretical yield into 100%. Now, for example, if you are synthesizing a compound B from a starting material A, and during the synthesis, if you generate another byproduct C. So percentage yield doesn't count for the byproduct C. That is where this atom economy concept comes, because green chemistry emphasizes that there should not be any byproduct. Or green chemistry says that you cannot neglect the formation of byproduct. You have to consider it. Now, so if it is a term, actually atom economy is a term that emphasizes that how much or the amount of certain material that get consumed in the product. That means we anticipate that all starting materials should get consumed in the desired product. There should not be any unwanted byproduct. So that's why percent atom economy say that formula weight of the atoms utilized divided by formula weight of all the reactants used in the reaction into 100%. So that means I'm going to show you an example, like a reaction with 100% yield may not necessarily be 100% atom efficient, because the atom efficiency may be very low. So I'll tell you, after listening to my lecture, you please look at the Wittig reaction. You will get a sense that Wittig reaction, those Wittig reactions which are giving 100% yield, but look at the enormous amount of byproduct from the reaction. So now I'll not take much time, because a lot of time left. So anyway, if we organic reaction, rearrangement, elimination, the atom economic atom economic, because there is no, I mean, it's a rearrangement. That means there is no byproduct formation, possibility of byproduct formation in a rearrangement reaction. Similarly, in addition, for example, the last one, if you look at that, how to say, butadiene with ethylene, it's a Diels-Solar reaction, and we get the cyclohexane. So there is no formation of byproduct. That means they are 100. We can say that they are 100% atom efficient reaction or atom reaction. Now, if you go to the substitution reaction, as the name suggests, the substitution, that means they are the living group. So in that case, definitely it cannot have 100% atom economy. For example, I'll show you how to calculate atom economy. This is an example of how to say reaction of benzene with ethyl bromide in presence of KLCl3 to give ethyl benzene and the byproduct HBr. Now, how we calculate percent atom economy? For example, we first write the reactants. It is first on the extreme formula with C8H. Formula is C8H11 Benzene has 8 and totally one it's a product of ethyl benzene. Now, if you see from this benzene to the ethyl benzene, only one H is missing. That is C6H5 is utilized. Similarly, from ethyl bromide, ethyl group is utilized. Bromine is not utilized in the product. So formula weight of the utilized amount is 77 plus 29, it is 106. And unutilized, it is not necessary for this atom economy calculation, but to have a knowledge on mass balance. That means if you calculate the unutilized and utilized, you should get the reactant formula weight. So, but we just see the utilized amount divided by reactant formula weight. So there we see the atom economy is only 56%. Similarly, elimination, they are the worst reaction from green chemistry perspective because it gives a lot of byproducts. And if you, I don't know whether you will be able to see this lecture later, but if you see it, you can see this elimination reactions. This is an example. If you calculate it, you will see the atom economy is only 40%. So this is definitely not a green reaction from green chemistry perspective. Now, I'll give you a real example of ibuprofen synthesis. Earlier, ibuprofen, you know, it is available as, how to say, Brufen 400 or Brufen 200. So earlier, the first synthesis was by a Booch company. It is called a Brown synthesis because the atom economy is very poor. Starting from isobutyl benzene with 1:1 stoichiometric ratio of aluminum chloride with acetic anhydride. And after these 6 steps, you get ibuprofen. So if you calculate, this table is there. I'm not going to explain the table. If you calculate the percent atom economy, it turns around 40%. But then alternative green procedure, if you look at this one, so are you in this slide, alternative green procedure? Can anyone tell me? Yes, you are in this slide.
Yes, sir.
Alternative green procedure,
Yes, sir.
right? Okay,
Yes, sir.
fine.
Yes.
Okay, fine, fine. Thank you. So, in this slide, you can see the alternative green procedure involves only 3 steps, and they use hydrogen fluoride in catalytic amount, and most importantly, this catalyst can be recycled. So, only 3 steps involvement you get from isobutyl benzene to ibuprofen. So, this is called a green procedure. And if you like calculate the percent atomic economy, you can see percent atomic economy is 77%, much higher than the Booch company's Brown synthesis. And even if you go back to the previous slide, if you can regenerate the acetic acid generated, if you can recycle the acetic acid generated in the first step, the atomic economy will be even 100%. So this is very ideal green synthesis, alternative green synthesis of ibuprofen. So there are many other examples. You will find it in the books. So I'll give you just last one example that about atomic economy. That this is a real example where you will see a reaction with high yield. 100% yield, but with very poor atomic economy. For example, the cracking of 14.2 gram of decane produces your desired product is ethene, 2.8 gram of ethene as the desired product, with the production of octane as byproduct. Calculate the percentage yield and percent atomic economy of the reaction. Now, like
कोई नहीं है सर आपको ऑडियो नहीं आ रहा है
hello.
सर you are mute
Hello.
yes sir now
Sir,
it's
yeah,
Hello.
it's audio
That is coming.
Aisha, sir.
Okay.
Yes, sir. Yes, sir.
yes sir
Yeah. Can you see the slides?
Yes, sir. Yes.
So I am in the percent atomic economy calculation of this decane. So is it okay?
Yes, sir. Yes, sir.
Okay. Sorry, networking issue. Anyway, I will. Okay. So these are all about atomic economy. So I will now quickly give you some example. Discussion on green solvents. So I'm in now green solvent slide. Now can you follow me?
Yes, sir. Yes, sir.
Okay. Okay. Okay, I'll quickly describe little things about green solvents. Okay, when we say a green solvent means, first of all, we know that most of the solvents we use are highly volatile. They cause environmental problem, as well as there are many issues related to solvents. I'm going to show you in 3 slides. So what are the alternatives of green solvents? We know that water definitely the best choice of solvent is cheap, readily available, and there are many other advantages of water. Then ionic liquids. These are the 2 issues I'm going to discuss. Then we have polyethylene glycols, and then we have supercritical fluids like supercritical carbon dioxide and supercritical water. Now, okay, if you look at this table, can you see this table? VOC is just toxic to Cephalon.
Yes, sir.
Okay,
Yes, sir.
so if you look at this table, that like I have shown, like green color, they are recommended. That means solvents like this, because daily in our laboratory we are using all these solvents. So, but there are some solvents, like if you look at the orange color, problematic or hazardous. So that means up to certain limit they are okay to use. I mean, they do not harm you, but if they exceed the limit, it will harm, create a lot of problems to the environment as well as to the human being. Now, there are some solvents which are hazardous or highly hazardous, like halogenated solvents like chloroform, dichromethane, DC, nitrogen, etc. So we'll, in the next slide, we'll see some of the danger diseases caused by the solvents. Benzene can cause
So you were not audible.
Sir, you are not audible. Hello, sir. Hello.
Can you hear me?
Yes, sir.
Yes, sir.
Okay, so can you see the slide?
Yes, sir.
Okay. It is giving a lot of problems. Anyway, so okay, now water, we know that it has a lot of advantages as solvent. It is also called universal solvent. Is gone again?
No, sir, it's visible.
Oh, it is visible. Okay. So it has advantages. We know, inexpensive, non-flammable, non-toxic, and it is highly polar and all these things. Then question is, why don't we use water then for all the organic reactions? Because we cannot use it. There are advantages we know, but what are the disadvantages? That all starting materials or organic reactants are not soluble in water. That is one disadvantage. So we cannot use always water for organic reactions. And another important difficulties with water as solvent is that most of the catalysts, they get deactivated or decomposed in water. I mean, they lose catalytic activity. So these are the 2 disadvantages of using water. Now, that option is ionic liquid. So I'll tell a few things about ionic liquid, then I'll stop. Okay. So now, ionic liquids, as like sodium chloride, potassium chloride, they are same. Only difference is that they are organic salts composed of organic ions and organic or inorganic anions. And because of the large size of cation and anion, they cannot form a uniform crystal lattice. That's why they become liquid at below 100 degrees centigrade. And there are some ionic solids which are liquid. That's why we call it as ionic liquid. And they are liquid at room temperature. We call it as RTIL. That means room temperature ionic liquid. Now, some of the examples are like I have shown it here: cations like 1-butyl 3-methyl or 1-butyl pyridinium. Similarly, anions like hexafluorophosphate, tetrafluoroborate, etc. So I will quickly show you the synthesis. How, and because it is very easy, only a two-step procedure, and there is no purification required. That is one of the another advantage. So synthesis is like we just take suppose 1-methyl or N-methyl imidazole. We add how to say haloalkane like butyl bromide. We get this salt, and then suppose if you take a bromide, how to say butyl bromide, you will get this N-alkyl, N-methyl, N-butyl imidazolium bromide, and that is not liquid at room temperature. So then we can increase the ion size by tetrafluoroborate or hexafluorophosphate to get this ionic liquid. Even the first step also, this is ionic liquid. But only thing is that you need a little bit high temperature to carry out the reaction, because then only they will become liquid. But at this stage, that last one, it is already liquid. So for example, I'm giving an example of synthesis of BMIM-BF4. What BMIM stands? That is butyl methyl imidazolium tetrafluoroborate. So and the synthesis started with imidazole reacting with butyl bromide. There is no solvent required. You just add these two substrates and just a little bit heat it up. You get this after around, it takes around 6 hours. You get this N-butyl N-methyl imidazolium bromide. At this stage, it is solid, not liquid at room temperature. And if you replace this or exchange this bromide with tetrafluoroborate, it becomes BMIM-BF4, and you get this ionic liquid. And it is known as butyl, and then nomenclature is almost like coordination compounds. Cation ends with IUM and anions end with ATE. That means butyl methyl imidazolium hexafluoro or tetrafluoroborate. So, and now this is important melting points of ionic liquid. As you can see in this, are you in this slide, melting points of ionic liquid?
Yes, sir. Yes, sir.
Okay. Then if you look at these salts like sodium chloride, potassium chloride, their melting point is very high, 803, 772. But if you go to the imidazolium, like methyl imidazolium chloride, its melting point is 125. And if you increase the alkyl size, cation size, melting point will go even down. Like for example, if you change 1-methyl and then 1-ethyl, its melting point is 87, and then 1-methyl with 1-butyl, its melting point is even going down to 65. Similarly, anion size plays an important role. Now, earlier you can see the chloride. If you replace this chloride by anions like borate, hexafluorophosphate, chloroaluminate, that you can see the melting point comes down from 87 to 6 to 7. So that means they are really liquid at room temperature. So, but when was it discovered for the first time? In 1914, like first liquid was discovered, it is ethyl ammonium nitrate. But its melting point is 12 degrees centigrade, so it is an ideal ionic liquid used for reactions. But later, its use was restricted due to explosive nature of this ionic liquid or this compound. People did not think much about this use of ionic liquid. But then 1980, the first generation ionic liquid, which are a little bit moisture unstable or unstable, the chloroaluminate ionic liquid was reported. Then, after 10 years of research, the first air and moisture stable ionic liquid, ethyl methyl imidazolium tetrafluoroborate, was reported. And then, after 10 years, in 2000, the first example of task-specific ionic liquid was reported. Now, what is task-specific ionic liquid? We know ionic liquid. What is task-specific? That means because ionic liquid so far we were using as a solvent, but what people started thinking about that, whether it can work as a catalyst also, I mean bifunctional. It will act as a solvent, at the same time it will act as a catalyst, or it will act as a base, or it will
Can you hear me?
Yes, sir.
Can you hear me?
Yes, sir.
Okay.
Yes, sir.
Okay, I'll finish in maybe. Okay, so
Yes, sir.
okay, anyway. Okay. So what are ionic liquids so much special today? I think a lot of research is going on nowadays on ionic liquids as alternative green solvent over conventional organic solvents. So I am in the slide desirable properties. Can you follow me?
Yes, sir.
Hello, anyone? Can you follow me?
Yes, sir.
I am in
I
the
can follow
slide
you.
desirable properties.
Yes, sir. Yes, sir.
Hello? Can you follow me?
Yes, sir.
I'm in
Yes,
the
sir.
desirable.
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Hello?
Yes, sir. You are audible.
Okay, so I'll down this share the slide. Okay, so can you see the slide?
It's loading, sir. Yeah, it's visible.
Okay. So it is in desirable properties, right?
Yes, sir.
Hello?
Yes, sir. I can hear you. Yes, sir. I can see the slides.
Hello?
Yes, sir. I can see the
Carry on,
slides.
carry on. We can hear you, Digandada. Carry on.
You can see me, right?
Yes, sir.
Can you hear me?
Yes, sir.
Hello?
Yes, sir. I can hear you.
Yeah, I think. Okay, so if it disturbs again, I'll stop you. Okay, you can go ahead with the next speaker. Because my internet is giving some problem. I don't have much to tell anyway, so I'll just slide. So can you see the slide now? Can you see the slide?
Yes, sir.
Can you hear me?
Yes, sir. Yes, sir, I can hear you.
Can you hear me?
Yes, sir.
Yes, can you hear me?
Yes, sir, I can hear you.
Okay. I'll not do any slideshow now. You can hear me still?
Yes, sir.
Hello?
Yes, sir, I can hear you.
So, because I don't have much, it's okay. I don't have much to tell anyway. Because of networking issue, I really apologize. And so, these things, if those students who want to know more detail, you can go through my book or any other green chemistry book, and you can email me also. I'll be very happy to reply. So my email ID is mentioned in the first page and the opening slide. So thank you again for giving me this opportunity. I could not deliver well, but anyway, thank you for this. So please go ahead with the next speaker.
Sir, thank you for your talk. So we have a question from a student, if you can, if network permits.
Okay, network permits. Go ahead. Yeah.
Hello.
Yeah, please go ahead.
Okay, sir. So the question is, sir, as you have mentioned. Okay, so the question is, as you mentioned that elimination and substitution reaction have less atom economy, right? So is there any alternative method to increase the atom economy of such reactions? Hello, sir. Am I audible?
Hello.
Hello. Yes, sir. I can hear you. Hello. Hello, sir. Can you hear me? Okay, so students, sorry, because of the network issue, we could not address your question, but we must thank Dr. Diganta Sharma for his talk. But yeah, we are sorry for the network issues. Okay, so our next speaker is Dr. Anupol Borua, again from Dibrugarh University. He is currently an assistant professor. So let me give you a brief introduction of Dr. Anupol Borua. So Dr. Anupol Borua did his master's degree from Department of Chemistry, University of Delhi. He also did his PhD from Department of Chemistry, University of Delhi. And his present area of research work are in silico protein designs, protein folding, misfolding, etc. And he's also a brilliant academician like Professor Diganto Sharma. So now I would like to invite Professor Anupol Borua to please present his work. Thank you, sir.
Thank you, Neha.
Thank you, sir.
Okay, so I'm audible and I'm visible also,
Yeah.
probably.
Yeah.
Okay. Good morning, everyone. And I'd like to thank Neha for the nice introduction. And at the very outset, I'd like to thank Okay, so religions have a very simple answer to this, that okay, gods have created everything, starting like stories like Adam and Eve and many other stories from different religions are there, and it's about creation, which is called creationism. And similarly, in a parallel thing from science, we have theories like Darwinism, right? Where it's about evolution, starting from we all have a common ancestor, and from that common ancestor, through natural selection, actually we have reached to this step. Darwinism is not exactly about origin of life; it is actually origin of species, because whatever is the first ancestor, if it is origin of life, then where from that first ancestor came from. But yes, creationism and Darwinism goes parallelly. And then we have the practical question of life, that, okay, now we have life, then what to do with life? Some people, different people have different perceptions regarding life. Some may have say that, okay, God has a plan and purpose for everyone, and so we don't have to worry about what to do. God anyway has the plan. Some may say that, okay, there is no purpose to life at all, so we have to just enjoy. You only live once. So that is another way of thinking about life. And maybe not, some may say that, okay, no God-given purpose, but we can have our own mission in life and dedicate our whole life to that mission. And for some, in fact, life is just a path to either heaven or hell. Whatever you do in life, based on that, actually you reach heaven or hell. So this is about what to do with life, different perceptions that we have. But what science says about different hypotheses about origin of life. Okay, one of the theory is abiogenesis. Abiogenesis is about we in the early age of the Earth, there were like inorganic molecules like methane, not inorganic, small molecules like methane and hydrogen in the atmosphere. And what happened actually is that through lightning or volcanic eruption, these molecules actually reacted and formed the life forms through abiogenesis. So this is one hypothesis. All these hypotheses that I am talking about now are actually no one is proven and or disproven. Okay, so this is one hypothesis. There is another about chemical evolution, and in chemical evolution we have two different types. One is the genes first approach, where small inorganic molecules that existed in the beginning of Earth's creation, those molecules actually reacted to form genes like RNA molecules. I'm visible, right? I like audible?
Yes, sir.
Okay, fine. So genes first is the approach where the inorganic molecules combine to form RNA, and then RNA leads to enzymes, and enzymes leading to metabolism. So the metabolism actually gives you the idea that life has formed. So it starts from genes. The other belief is that metabolism first. You start with inorganic molecules. Those inorganic molecules comes in an order, and that order actually leads to metabolism first, and that metabolism leads to RNA, and RNA leading to proteins. Okay, proteins and enzymes. So these are two different thought processes and hypotheses about creation of life. Then there is another that we are the aliens. This is another viewpoint that, okay, in the early period, probably some asteroids where life forms were there, very preliminary life forms were there, which collided with the Earth, and those life forms survived that collision, and from there on we have reached this position now. So although again this is not an origin of life idea, it is origin of life in Earth idea. Anyway, all these approaches are there, but these are most of them are from biology, idea from biology. Okay, so being chemist, and since chemistry is a very integral part of life, formation of life. So do we have anything very close to us which can give us some idea about creation of life on Earth? And that's a very very familiar field that we can utilize to understand the formation of life, although not proven, but there are many promising ideas coming from this field, and the field is thermodynamics. Whenever we talk about thermodynamics, there are many terms and many equations that comes into mind, like system, surrounding, energy, heat, like enthalpy, entropy, reversible, irreversible, spontaneous, and of course the laws, the zeroth law, first law, second law, third law, all those laws are also there. So what actually thermodynamics deals with? It actually deals with what we see in day-to-day life, the macroscopic world. Anything macroscopic, thermodynamics has the answer to. Okay, so more specifically, if we say in a scientific terms, thermodynamics is the study of transformation of energy in different processes. So starting from the morning tea, the hot tea, if you keep it in the room and it slowly cools down to the room temperature, that can be explained by thermodynamics. Probably in this time of lockdown, you are missing this Bunsen burner, which actually burns the gas and produces heat. The reaction mixer that we always deal with, in the laboratory. In between, we deal with the laptops and mobiles. And in fact, the library session that we start with high order in the mind, but later on, slowly we just go into disorder. The state of the mind goes into disorder, and we go into sleepy mode. And in fact, we, the human beings, our ancestors, every living organism, every non-living organism, and art, everything follows thermodynamics, and in fact, the whole universe follows and must follow the thermodynamic laws. So can we find anything from thermodynamics to see where the life has originated in this Earth? So before going into that, we will need some ideas of thermodynamics, very fundamental ideas. Probably all of us have gone through all these ideas, and but we will have to refresh those ideas here. So first thing is the system and the surrounding. System is the part of that part of the universe of which we are studying the properties. Okay, and surrounding is anything in close contact with the system that we call as surrounding. Now, this is a very common equation. Delta U is equal to Q minus W, where delta U is the change in energy of the system, Q is the heat absorbed by the system, and W is the work done by the system. I write here that the important thing that you have to notice here is that I'm writing it as delta U. That means a change in the energy from when the system goes from one state to the other state. But I don't write delta Q and delta W, because Q and W itself is associated with the process, not with the system. Okay, so Q is the when we talk about W, it's the work done by the system. I have used Q minus W, and in many books you will see that it is Q plus W, so you may get confused. It is simple sign convention. In my presentation, I have chosen work done by the system to be represented by W. So when work is done by the system, so energy is lost by the system. So it comes as negative of W for the energy of the system. And Q is heat absorbed by the system. Okay. So work, what is work then? Work is a quantity that flows across the system boundary during a change in state of the system that can be used to move a mass in the surrounding up or down. Okay, we have to if work transmits from the system to the surrounding, we can use that energy to move a mass in the surrounding up or down. Okay, and heat is because of temperature difference between the system and the surrounding. Okay, so heat will flow from the system to the surrounding if the from surrounding to the system if there is a temperature difference existing in the between the system and the surrounding. So the thing that we have in this slide that I want to emphasize here is that work and heat are not associated with the system itself. It is associated with the process. Okay, if there is a process happening, there can be heat exchange or work done, but we cannot say that the system has this much work or the system has this much heat. That is not the thing. The system has energy, and that energy can be used for heat transfer or work done. Okay, so you have to be clear about that. And with these ideas, actually, we have seen experientially, and we have to understand that thermodynamics is a completely experiential science. We have to experience, and then we can see what is going to happen and what is not going to happen. And one of the important observation which has never been violated is that energy of the universe is conserved. Okay, that is the first law of thermodynamics, that energy can never be created or not need to be destroyed. So this is the first law. And then I will again go for work and heat. I try to understand this physically, what we mean by this actually. So we have this Bunsen burner, and we have the system inside the box. It's a gaseous system. Inside the white box, assume that there are molecules of gas. And the box, the upper wall, it can move up and down if required. Okay? And that upper wall has a mass on it, as shown by the blue box. So if we hit this system, gaseous system using the Bunsen burner, what will happen? That energy will get transferred from the Bunsen burner to the gaseous system, and the molecules of the gaseous system will become energized, and those energy can be utilized to work on the surrounding, and therefore it can push the upper wall to a higher, to a greater height, as shown in the animation. You can see, and the mass is moved up, right? So important thing here is to notice that work produces ordered motion in the surrounding. Okay, so when you are heating the system and you're giving energy to the system is working on the surrounding, and the whole mass, all the molecules in the blue block are moving upward direction. So that means it is a ordered motion in the upward direction. So work always produces ordered motion in the surrounding. So what happens with heat then? We start with the same system. There are a few differences though, is that the upper wall is no more movable. It is it can permit heat though. Wall is not movable, it can permit heat. And in the above container, instead of the mass, we have now some water there. Okay, so now again we heat the system, we give energy to the gaseous system. The system now has more energy, and that energy can be now transferred through the wall to the water molecules in the form of heat. Okay, and what will happen to the water molecule in the process? That it will obviously the temperature will increase, and the motion of the water molecules will become random, more disordered, and it will become higher energy, and it will become more disordered motions. So what again, the important thing to notice here is heat produces disorder. Okay, so the thing that we are trying to understand, emphasize here, is that work is producing ordered motion in the surrounding, while heat is associated with disorder. So this idea will help us in understanding later on why I am emphasizing on this. And another important thing is that, okay, I want to point out here is that, okay, a light thing here, that in fact the English language, I think, that uses these two words quite scientifically. You can read the sentence. One has to work on his emotional balance so that he or she does not do anything wrong or idiotic in the heat of the moment. Okay, like if you want to have some emotional balance, that means some order in your emotions, then you have to work. And if you don't want to produce any disorder around you in the heat of the moment, that means you don't have to react in the heat of the moment. So like the words are being used quite scientifically in the English language also. So now one thing that I want to point out here, that the first law of thermodynamics, that energy can neither be created nor be destroyed, that's the idea, actually disallows some of the processes like which tries to generate energy or destroy energy. Any process that tries to create energy or destroy energy will not be allowed by the first law of thermodynamics. But at the same time, it cannot actually differentiate between spontaneous process and non-spontaneous process. What I mean from here is that, like the cup of tea that I talked about, when you keep the cup of tea, the hot cup of tea in the room, the tea loses energy in terms of heat to the surrounding, and it comes down, the temperature of the tea comes down to the room temperature after some point of time. So this is the natural spontaneous process, and this is allowed by the first law because the energy, whatever energy is getting transferred to the surrounding, it is increasing the heat in the surrounding also. Okay, but the opposite phenomena never happens spontaneously. We have never seen that a cool cup of tea is becoming hot after some point of time. But if you see in that process also, neither energy is getting created nor energy is being destroyed. If we imagine the situation, because the cool cup of tea actually have to take up energy from the surrounding, and that energy will be utilized to increase the temperature and in the cup of tea. So energy is neither being destroyed, neither being created, nor being created. But still, this we have never seen this happening ever. So this is not a spontaneous process. So first law does not differentiate between spontaneous and non-spontaneous process. So to understand which process are going to happen spontaneously and or going to happen, not going to happen spontaneously. To understand these things, we need some other ideas. And to get those ideas, which of the processes are going to happen spontaneously, to get these ideas, we have to again depend on some experiences that we have. And we can get the ideas from some impossible machines that we cannot ever make, because people have tried to create these machines, but they always have failed. Okay, so some of the machines, I will mention two machines here. Machine one is there is no engine can be designed that operates in a cycle and takes up energy from only one reservoir in the form of heat and converts the whole energy into work. Okay, with only one heat reservoir, we cannot take up heat from that reservoir and convert the whole energy into work. That is not possible in a cyclic process. And in fact, to do some positive work in the surrounding, an engine at least requires two reservoirs. Okay, so this is the requirement. And in producing work, why do we need actually two reservoirs? Experientially, we have seen we need two heat reservoirs, because from one we will take up the heat energy and we will convert some of it into work, a part of it into work in the surrounding, but remaining energy we have to lose it to the surrounding second heat reservoir. So that has to be done, then only a machine can be created. This is by experience we have seen, and this can never be violated. Okay, so this is one of the impossible machines. The other one is that no engine can be designed that operates in cycle again to have its only effect as taking up energy from a cold source and releasing it to a hot source. Okay, so that means you cannot design an engine which will take up energy from a cold reservoir. Temperature is lower, you take up energy from that and put it into a hot reservoir. That is not possible. That experientially we have not seen that happening ever, and that is not possible. So why we are discussing these machines? Because these machines, since these are impossible machines, that means the process that they are trying to generate is also impossible. That means they are non-spontaneous processes. So definitely the spontaneous processes will be opposite of this. And if you look into the ideas of these two machines, they both say that if you want to have a spontaneous process, actually, there has to be some amount of energy getting dissipated or energy getting distributed in the process. Okay, energy cannot get concentrated in one place. Okay, energy has to be distributed. That is the requirement that is being given by both the machines. Actually, if you look at the machine one, that means if you want to convert some heat into work, at the same time you have to lose some heat to the surrounding. That means you have to distribute some energy to the surrounding. You cannot just do work. You have to distribute some energy. Similarly, for machine 2 also, you cannot take up energy from a cold source to the hot source. That means you cannot concentrate energy. Already energy is higher in the hot source, and if you are trying to take up energy from a cold source, which is lower energy, to the hotter energy, that means hotter source, that means you are trying to concentrate energy in a certain place. You are not trying to distribute the energy. So that is why it is not a feasible process. So in all the spontaneous processes, energy has to be distributed. Energy has to get dissipated. That is the first thing. So with this idea, we have to go to the engine that can be created. It's a very commonly and widely discussed heat engine, which we call the Carnot cycle or the Carnot engine. We would like to discuss this because if we discuss this, we will see that there is a function or a property of the system that can be utilized. By seeing the value of that property, we can actually say that which process is going to be a spontaneous process or non-spontaneous process. So for that, we will go through the Carnot engine. The Carnot engine actually has 4 steps. First is isothermal expansion. Most of us already probably know this. First is isothermal expansion. We have shown the expansion in the the whole Carnot cycle in the diagram, so everyone can, I think, follow the diagram. First is the isothermal expansion, then it's an adiabatic. So in the first step, you have to take up heat, Q1 amount of heat from the heat reservoir shown in the red color, and the system shown in green goes through an isothermal expansion. Then next, there is an adiabatic expansion. In adiabatic expansion, since the boundaries do not allow heat transfer, so there is no heat change, I mean heat during the process. So, and then there is isothermal compression, and finally an adiabatic compression to reach the original state. So again, this is a cyclic process. Okay, so in each of the step we have done some work, W1, W2, W3, and W4. So the total work done during the process, during the whole cycle, is equal to, as shown in the expression of W, which is total work done, and Q, the heat during the whole cycle, is Q1 plus Q2. Q2 is released, the heat is released to a reservoir as shown in the blue reservoir in the step 3, because we are compressing, isothermal compression, and in that we release some energy to the other heat reservoir. So you need minimum 2 reservoirs for this region. Okay, you have one reservoir at a temperature T1 and the other reservoir at temperature T2. Okay, so as the first law says, the energy can neither created nor be destroyed. So in a cyclic process where the system comes back to the original state, so delta U will be equal to 0. The energy change is 0. So delta U was equal to Q minus W. So now W becomes equal to Q. So the efficiency of this engine, okay, we can calculate as shown as epsilon, as represented by epsilon, which is W by Q1, the work generated by the engine divided by the heat taken up by the system from the heat reservoir. So since W is again equal to Q and Q is equal to Q1 plus Q2, we can put that, and we find that epsilon efficiency is equal to 1 plus Q2 by Q1. And the thing to notice here is that Q2 and Q1 both have opposite signs, because Q1 is heat absorbed by the system and Q2 is released by the system to the surrounding, to the second reservoir. Okay, so both of them has opposite signs. So Q2 by Q1 will have negative sign. So it is the efficiency will be always less than 1. So some energy, what does this mean is that some energy always dissipates as heat. No engine can have efficiency of equal to 1. And we can also show, I have not shown the derivation here, we can also show that the efficiency can also be related to the temperatures of the reservoirs, as shown by this expression, 1 minus T2 by T1. T2 is the temperature of the second reservoir, and T1 is the temperature of the first reservoir. So these two becomes equal. If we use these two expressions, we find that you can see step by step that Q1 by T1 plus Q2 by T2 becomes equal to 0. So in the cyclic integral of dq reversible, all these steps, I forgot to mention that all these 4 steps are reversible steps. Okay, so these so in the cyclic process, the dq reversible by T becomes equal to 0. What does this mean is that this dq reversible by T is a state function, because when it comes, it's in a cyclic process. That means when a system goes through different changes and comes back to the original state, this dq reversible by T term, whatever it represents, till now we have not discussed this, dq reversible by T does not change. That means this term depends only on the state, not on the path. So this is a state function, and this state function we call as ds is the entropy. We call this term as entropy, and this measures the disorder of the system. The entropy S actually can measure the disorder of the system. Why? Because as I discussed earlier, the heat of the if heat is released, it actually leads to disordered motion. And in this expression, you see that ds is defined as dq reversible by T. So it is the heat divided by the temperature. So basically, entropy is a measure of disorder of the system. And I want to mention here that even for irreversible processes, if you want to calculate the entropy change, you have to design a process, a corresponding process, reversible process, and for that reversible process, whatever is the heat dq reversible, that has to be utilized, because entropy is defined as dq reversible by T. Okay, even for irreversible process, it is dq reversible by T. So that has to be taken care of. So now we know that entropy is a measure of disorder, and this entropy can be, the value of this entropy can be an indicator of a spontaneous process. So we will see how. Okay. Now using, we will use two engines now. One is the Carnot engine, and another is a different engine, which can have a very complicated engine, or it can be a reversible engine or irreversible engine. It doesn't matter. We just have one Carnot engine and another engine, and we combine the two engines and form a composite engine. And for the Carnot engine, we have shown that dq by T, the cyclic integral of dq by T, is equal to 0. We have already shown it earlier. And now let's assume that for the other engine, since it is not reversible, not irreversible, and it can have many complicated cycles, many number of reservoirs, not just two reservoirs, all those are allowed. Let us just assume that for this engine, the cyclic integral dq dash by T is greater than 0. It is just an assumption. So for the whole composite engine, if we see the cyclic integral as shown in the expression, that will also be greater than 0. Now, let us assume that we create the Carnot engine. We don't do anything with the other engine, because we are trying to find the dq by T in the other engine. But what we do is that we play with the Carnot engine. We play with the size of the Carnot engine, and we make the size of the Carnot engine such that the work produced by Carnot engine is taken by the other engine, and the corresponding work produced is exactly balanced. Okay, that means in the whole process, no work is produced. So WC, which is the work produced in the whole cycle, is equal to the cyclic integral of dqc, will be equal to 0. So we can expand this dqc in cyclic integral as q1 plus q2 plus q3 plus q4 plus all the steps that it has, equal to 0. And as we have assumed, as we have shown that for the whole composite engine, that dq by T cyclic integral is greater than 0, and we can just separate those terms also, and we can show that q1 by T1 plus q2 by T2 plus q3 by T3 and go on, we get that is greater than 0. So these two equations, if you combine, that q1 plus q2 plus q3, this is equal to 0, and these ratios, the summation of these ratios is greater than 0. This is only possible when the positive heat, that means absorption of heat, is divided by lower temperature, right? And the negative heat is divided by higher temperature. Then the negative terms will be having lower magnitude, so it will be greater than 0. The summation of these ratios will be greater than 0. So now you see, is this possible? Is this possible? Because we are saying that when we are absorbing heat, we are absorbing heat from a source which has lower temperature. Okay? And we are saying that when we are releasing heat, negative heat means we are releasing heat to the surrounding, and we are releasing it to a higher temperature source, which is not possible. We have shown in the impossible machines that transferring heat from cold source to a hot source is not possible. So that means the assumption that we have started with, that the cyclic integral of dq dash by T of the other engine is a wrong assumption. That means dq dash by T cyclic integral has to be less than equal to 0. That the only possibility is that it has less than 0. Now, if the engine is reversible, we get 3 that engine is reversible or reversible. If it is reversible, in that case, if we assume that dash by T is 0, Okay, and now we reverse the process. Since the engine is reversible, we reverse the process. We all Q's have opposite sign, and so therefore the cyclic integral dq dash by t becomes now for the reverse process, which is again not possible. So for a reversible engine, for whichever material you use, whichever how many number of complicated cycles you use, the cyclic integral of dq reversible by t will be always equal to 0. And for the irreversible process, the heat change in the irreversible heat change, I'm wrong. In a reversible process cannot change. So if dq reversible by t is equal to 0, the only option left reversible in other engine is reversible, then only option left is that cyclic integral dq by t is now less than 0. Okay. Again, let's hear a cycle, which is the overall cycle will be irreversible. In the first step, there will be an irreversible process going from system state 1 to system state 2, and then there is a reversible process from state 2 to state 1. That means it's again a cyclic process. In the first step, it's an irreversible process. The second step is a reversible process. So overall, it's an irreversible process. So for the whole overall process, if we calculate the cyclic integral of dq by t, as we have derived, we can show that the whole thing becomes less than 0. And the integration 2 to 1 dq reversible by t, we can replace that by ds, as it's the definition of the entropy change in the process. So now if we do the integration from 1 to 2 instead for the entropy, then it becomes, since it's a state function, it becomes the opposite sign, and it becomes minus integration from 1 to 2 ds, and it is less than 0. And so therefore dq irreversible by t, integration of dq irreversible by t is less than integration of ds, right? So entropy change for the irreversible entropy change is greater than the dq irreversible by t. Okay, this is an important finding. In a natural process, in an irreversible process, in a spontaneous process, entropy change will be greater than dq irreversible by t. Now, let's see for an isolated system. If the system is isolated, that means it is not interacting with the surrounding. So dq irreversible, if the system goes through a process, irreversible process, then dq irreversible will be equal to 0. And therefore, ds is greater than 0. So entropy change in an isolated system will be always positive for a spontaneous process. So this is an important finding, right? So all these observations, starting from the impossible machines to energy dissipation to entropy change in the isolated system, these actually gives us the idea that a spontaneous process, what will be the criteria for a spontaneous process? Okay, so entropy is a state function, so you can have the value of entropy, and from the value of the entropy you can say that which of the process is going to be spontaneous and which is not. So basically, second law of thermodynamics, we have different statements. From the impossible machines, we have the Kelvin statement that we cannot absorb heat from a reservoir, single reservoir, and complete convert it to work. That is not possible. This is one way of presenting the second law of thermodynamics. Other is that heat cannot flow from a cool body to the hotter body spontaneously. That is a second impossible machine that we talked about. Both of them actually means that in a spontaneous process, energy always dissipates. And the formal statement that we have derived in the process is that entropy of an isolated system always increases during a spontaneous process. But now the question is that we have derived that, that for a spontaneous process, there is a state function that we can rely on, and we can see the value of that state function, which is entropy, and we can say that the process will be spontaneous or not. And that means we are, and in the process we have seen that the entropy will increase. That means the disorder will increase. As I said, that entropy is a measure of disorder because it's about dq by t, q is about heat, q is about disorder. But the question now is that why disorder? Why the spontaneous processes actually prefers disorder? This why cannot be answered by thermodynamics. Thermodynamics always deal with macroscopic system. It gives us that what is going to happen, what is not going to happen, but why that is going to happen cannot be answered by thermodynamics. So that has to so why disorder that question if we want to address, then we have to rely on something else. And as we know that macroscopic system, although we see them, but those are made of all microscopic particles like atoms and molecules. And if we want to deal with the microscopic particles, then we have to deal with quantum mechanics. Quantum mechanics deals with those particles, and we can understand the particles in terms of that. And we can very easily understand that whatever the property of those particles, the average property we see as in the macroscopic system, right? That the property of the macroscopic system has to come from the property of the microscopic particles. And that relation, I can show that this microscopic wall, which is dealt by quantum mechanics, and the macroscopic wall, which is dealt by thermodynamics, there has to be a bridge to understand the question why disorder, or why anything, any why that we have with the macroscopic wall. We have to relate the quantum wall, macroscopic wall, through statistical thermodynamics. The bridge in between is the statistical thermodynamics. Because whatever property the atoms and molecules have, those properties, if we average up, that we see as the average property of the macroscopic system. So for any, whenever we are talking about average itself is a statistical quantity. So you have to go to statistics, and that is called statistical thermodynamics. And whenever we are talking about a property X, assume, and we are trying to find the average of X, then that can be calculated as X bar, which is equal to summation Xj. J represents a state of the system, or allowed state of the system. And if we relate it to quantum mechanics, it's an allowed energy state or allowed state of any microscopic particle. And Xj is the corresponding value of the property for that state. Okay, so this Xj we can obtain from quantum mechanics, and the X bar that we can gain from thermodynamics. What we cannot gain from quantum mechanics or thermodynamics both is the Pj. Pj is the probability of the Jth energy state, and that probability is given by statistical thermodynamics. So basically, this shows that we have only one goal in statistical thermodynamics, and that is not my view about statistical thermodynamics. This is given by Erwin Schrödinger. I like this view because if we say that the whole subject has just one goal, the complete mindset becomes much more positive, right? And we can have a positive outlook that, okay, we can handle because only one goal, and we become much more focused. So the goal is that we want to find the distribution of energy. Although in this lecture, we are not going to deal with finding the distribution. But yes, this goal can be achieved in two different ways. First is the time averaging. If we look at the system and the system evolves with time, you can see that the particles are moving. I hope all of you can see this. If anyone can give any input.
Yeah.
Yeah, okay. So the particles are moving at different time. The particles are having different positions. And if we have all these snapshots of this system at different times, we can calculate the property of our interest at different times, and we can have the average of this. This is one way, but this is a very complicated, very difficult way to do, because I will say why. Because there are n particles in the system, and all the particles are interacting, and all the particles have some force acting on it. So first thing has to get the time evolution of the system. First thing that we have to calculate is the force acting on all the particles, and then we have to calculate the acceleration using classical mechanics, acceleration on each particle, and then we have to, after some time t, we have to calculate the new position of all the particles, which is a very complicated process. And that too, we are talking about classical mechanics. We should use quantum mechanics because all these particles are microscopic particles. So if we use quantum mechanics, then obviously it's a problem of solving, wave function of n particle wave function solving problem, which is impossible. So this is a complicated way of doing time averaging. So instead, what we can do is an ensemble averaging. Okay, what we mean by ensemble averaging is that if we have a system of interest, this is an imaginary way of doing things actually. If we have a system of interest, we can imagine that there are n number of replica systems also. Okay, it is just an imagination. Okay, the replica systems are not actually existing. So we have a system and we imagine that there are n number of replica systems and all of them are existing in different allowed states. So for all these states, if we calculate the corresponding property of interest and we average it out, we also get an average for that property. So, and we have two postulates in statistical thermodynamics. The first postulate says that this time average and the ensemble average actually comes out to be equal. But there is a condition: only when the time that when we are time averaging, if the time is large enough, and when we are ensemble averaging, then if we are imagining the number n of the replica system is to be very large, infinite number of systems we are imagining, then the time average becomes equal to ensemble average. So if we just calculate ensemble average without thinking about the forces, the accelerations, the positions, if we, the forces and acceleration and interaction, if we ignore and we just have an ensemble, imaginary ensemble, we can have the corresponding average. So in this way, we can get the distribution. I'm not going into the derivation of the distribution. One of the very famous distribution is the Boltzmann distribution, which can be given as shown in the equation, where Pj is equal to e to the power minus beta Ej by summation e to the power minus beta Ej. The summation e to the power minus beta Ej we represent by Q, which is called the partition function. This is a very important term in statistical thermodynamics, but we're not going into the the significance of these terms now. Our goal is to find the interpretation of work, heat, and entropy through the angle of statistical thermodynamics. So now let's try to find the average energy of a system. As we have showed that for any property, we can have the average as shown by these equations. We have to multiply the probability with the corresponding value of the jth states, summation Pj, Ej in this case. And therefore, if we want to find the change in energy during a process, we get this expression, summation Ej dPj plus summation Pj dEj. So now, again, we can modify, we can rearrange these terms, and we can actually find, I'm not going into detail of the derivations, we can find that dE bar comes out to be summation Ej dPj minus TdV. Okay, this is from statistical thermodynamics. And we have a corresponding expression from thermodynamics, which says that dE is equal to heat plus heat minus PdV, right? Heat minus PdV. So if we compare these two, okay, basically what is heat and minus PdV actually represents work done, right? So one term is heat and one term is work done. And if we compare the terms coming from statistical thermodynamics and the term coming from thermodynamics, we see that summation Ej dPj actually represents heat and summation Pj dPj dEj represents work done. Okay, so now what interpretation can we have from this? So work done, as we saw that it is summation Ej dEj. So what we can see is that during when a system does a work, then the probability distribution, the Ej's are not changing. What is changing are Ej's. We have the term dEj, that means change in energy state, the value of the energy of the energy state. Okay, so when we are working on a system, the distribution of system over the energy states are not changing. What is changing is the value of the energy of the energy states. You can show this graphically, that we start with a system like this, that we have these energy states, and we have these black circles as the different systems of the ensemble. So different number of systems are occupying the energy states. Okay. Now, if we work on it, then the distribution of systems. In the ground state, there are 3 systems. After work done, also the ground state contains 3 systems. That way, the distribution remains exactly same, but the energy values have changed of the energy states. Okay. But what happens then with the heat? It is summation Ej dPj. Again, here we can see that when we heat a system, then the energy of the energy states remains exactly same, but what changes is the probability distribution of the systems over the energy states. It can be shown like this. If you heat the system, the distribution of systems over the energy states differs. Earlier we had 3 states in the ground state, and now we have 2, and likewise the distribution has changed. Okay, so now coming to interpretation of entropy, we had the interpretation of work and heat. Now coming to interpretation of entropy, these are the derivations. If anyone needs the derivations, I can share it with them, but I'm not going into the discussions now because we're running out of time. And finally, we get an expression for the entropy from statistical thermodynamics relating the entropy to probability distribution, as shown in the last expression, which is entropy is equal to minus kb summation pj ln pj. Pj, as I said, that is the probability of the jth energy state. We have related the entropy to the probability of a state, right? And now, if we come to an isolated system, as we have defined, we had our second law of thermodynamics in terms of isolated system. Again, here also we would like to bring in the isolated system. Now we have an isolated system, it does not interact with the surrounding, so all the energy states will have the same energy, right? The system cannot have different energy because it cannot interact with the surrounding. So all the energy states have same energy, so they are equally probable. So all the PJs for different energy states are equal, and if the number of states is equal to omega, then the PJ has to be equal to 1 by omega. Omega number of states having same probability. Only option left is that the probability has to be equal to 1 by omega. And if we put that into the earlier expression, we get that final expression for entropy for an isolated system can be expressed as kb ln omega. I am again emphasizing omega represents the number of states for the system that we are talking about in an isolated system. Okay, so how do we interpret this then why how we can interpret this equation to understand that why increasing entropy actually leads to disorder, or why a system actually prefers disorder in a spontaneous process. You can see this these diagrams. We have 161 yellow boxes in each of these diagrams, okay, and 64 red boxes, and total we have 225 boxes. So if we try to arrange in different ways, the total number of ways that we can arrange these type of 64 red boxes, 161 yellow boxes will be almost equal to 1.3 into 10 to the power 57 as given by this expression. So we have so many number of ways, but out of all those arrangements, one of the arrangement is shown on the right. You can see, okay, it's a kind of an ordered arrangement of the red boxes, of red and yellow boxes. Red boxes are concentrating at one place and forming a structure like a human being, okay, and this is an ordered state I'm talking about, and there is only one possible way to get this. Okay, all the red boxes has to come to these positions, and there is only one way. So there is only one way possible out of 1.3 into 10 to the 57 ways. So the probability you can see for this state is very low. And all other states, only four I am showing, but all other states, 1.3 into 10 to the 57 minus 1, all other states leaving this ordered state are disordered according to us. It's not forming exactly this human being inside the diagram, right? So it's kind of a disordered thing, and all those states, 1.3 into 10 to the 57 minus 1 states are there for that disordered thing. So the probability, if we calculate, it almost becomes equal to 1, as we have shown in the expression below. Okay, so basically you have, because of the number of states, the omega for this disordered states is very, very high. So we have very high probability of the system being in a disordered state. Then being in the ordered state. Okay, and since it is a disordered state, the system has very high probability of being in a disordered state. So in a spontaneous process, the entropy increases. We have higher number of states available. So S will be KB, ln omega. So higher value of omega, higher entropy, and we see that because of higher entropy, we are living a higher probability, higher number of states, we are living in the disordered states. So basically, because of the higher number of states, the system can be in any of those states. It can be in the first state, second state, third state. So that leads to disorder. And because of higher number of states, there's higher probability and higher entropy. So basically, higher entropy means higher disorder. So this is the reason that, yes, we get that entropy has to increase. That is from thermodynamics. But why, if entropy increases, that leads to always disorder? That comes from statistical thermodynamics. Okay, this way. So this is the interpretation of entropy. Now coming back to why life then. As I have shown here that in the box itself, in the diagram itself, arranging the boxes to form a human-like structure, bringing it to an ordered state is so improbable. Like having a real life human being or any other organism, for that matter, creating that much of order, and that is happening spontaneously. Why that is happening then? Is it against thermodynamics? So again, we come back to Schrodinger. He has a book. He dealt with this topic, and his book called "What Is Life?" I've given the image here, and he proposed that probably for life we need a periodic crystal. I'm not going into detail of those. And later on, come out. Till then we didn't have the idea of DNA. We had the idea of DNA, but what is the structure of DNA? All those things were not known. But Schrodinger said there has to be an aperiodic crystal which takes the information from generation to generation. And later on, we saw that that aperiodic crystal has to be the DNA, right? So he could predict all these things. And he also proposed that large size of organism can, compared to the atoms and molecules, is necessary for life processes, because statistical processes that follow statistical laws needs large number of small molecules. Okay, then only. So if large number, so the obviously size will be less. So these things he predicted rightly. But what he went wrong, or at least confusing to the audience, is that he said that life is a negative entropy process, and he said that although it does not violate the thermodynamic laws, because entropy change, when we talk about it, has to be positive entropy change, then it has to be isolated system. But life is not an isolated system, so it does not violate the laws of thermodynamics. But probably we may need more natural laws, maybe new natural laws has to be required to explain why life is existing on this earth. But that was a confusing approach, and but in a very recent development, it's the first time appeared in 2013 actually. We have seen there's a new hypothesis for the formation of spontaneous life in us. This young man, Jeremy England, who is probably around 37 years old, from MIT, has proposed this hypothesis. And he says that the process of life is a spontaneous process. And he utilizes all these ideas from statistical thermodynamics. This is very interesting. And he utilizes the Boltzmann equation and entropy, which is S equal to KBL and omega that we have derived here. Okay? And he utilizes this for far from equilibrium processes. Life is not in equilibrium. We are moving ahead in the process. We are far from equilibrium. So he has derived the corresponding equation. He has not derived. He has utilized the corresponding equation for far from equilibrium processes and shown that life is actually energy dissipation driven adaptation. What we are good at as life, what we are good at is that we absorb energy actively from any source, any energy source like the sun, like all the foods. We can absorb energy very actively, and we can distribute it very actively, both of them. Okay, you can for an example I can show. In a room, if you can put 10 chairs, and the heat, you can see the temperature in the room. Now, instead of the chairs, you put 10 human beings in the small room. Okay, we dissipate so much energy that the room slowly becomes hot, right? So the life forms, and that happens with all the life forms. Life forms are very good at dissipating energy, and which is the requirement of the only requirement of the second law. The energy has to be dissipated. So therefore, this young man says, that hypothesize that energy or life, since it can dissipate energy very actively, therefore life happens spontaneously on this earth. This is the idea. This is not yet proven. Only computer simulations is being done. In 2017, we have some support for this hypothesis, but not yet proven. Okay, so in fact, for self-replication or reproduction, also this hypothesis gives us some idea. But we have less time to discuss all these things. So now we have the understanding, probably at least a new theory or idea from thermodynamics and statistical thermodynamics, that why life is existing on this earth. But what to do with life? This slide is not a scientific slide, I would say. Since I'm dealing with the BSc students, I thought I can draw metaphors from thermodynamics, because thermodynamics is a very beautiful subject, and we can draw many metaphors into the real life, and that can be applied to the society, to the world. Okay, so obviously, as we have seen, that nature has a purpose for us, probably, and the purpose is to dissipate energy. That is the only purpose that nature has given us. We have to actively take up energy from source, make it more disordered, make the universe more disordered. So nature will anyway produce disorder out of us. And we can already see in the society, in the world, that how much disorder we are actually producing. The things, the incidents that are happening in the recent times that says that how much disorder we are actually producing. But due to evolution, we are human beings, right? We have a certain level of consciousness through evolution, which is not comparable to the other life forms in Earth. We have a higher level of consciousness. And with that consciousness, we can understand nature, we can understand natural laws, differentiate work and heat, differentiate order and disorder. So instead of just producing disorder as nature wants out of it, we can, along with disorder, that anyway we have to produce, along with disorder, we should try to produce some work during our lifetime. The efficiency of this machine of life that we have, the heart, the kidney, the liver, all these are machines, and these also have some efficiency. And along time, these efficiencies will anyway go down. Everyone at a certain age, our machines will have very, very low energy to produce any work. We will be producing only heat and no work. So we have the first thing is that we need to take care of our health so that we can keep our efficiency high for a longer time, and at least try to absorb more energy from wherever we can. Try to absorb more energy, more motivation, more focus on a specific goal, and produce significant work in that direction. Disorder will anyway prevail. So this is it for this lecture. Thank you.
Oh, hello, am I audible? Yeah. So thank you, Dr. Anupal Barua sir, for such a wonderful presentation on statistical thermodynamics from the perspective of life. It was quite interesting. So now we have some questions from student. So the first question is, Q and W are not state function, but
yes,
become state function under certain conditions. Why?
No. Q and W, they are not state function. They are, they can actually, you cannot say that a system has heat or a system has work. That is never possible, okay? It is always energy that a system has. Okay, a system cannot have heat or a system cannot have work. If you see in the process that, okay, the entropy is a state function, which is defined by dq by t cyclic process going to zero, it seems that it is being a state function in that process, the cyclic process. But actually, heat and work, these are not a state function; those are only path functions.
Okay, so we have another question from a student. How heat and work is not associated with the system?
That is what I am again saying, that what is associated with the system is the energy. So the system can absorb heat from the surrounding and increase its energy. So heat is the process. Heat is related to the process, which is getting transferred from the process is that the energy is getting transferred from surrounding to the system. That is the heat. So heat is associated with the process, and when the heat is absorbed by the system has now more energy. It does not have more heat, because even if you absorb heat, energy as a heat, you can convert that into work in the surrounding. Okay, so again, when we're talking about work, it's about the process. If you want to do some work, that means you have to lift weight in the surrounding. That's the process. So the work is associated with the process, and in doing so, you have to utilize some of the energy of the system. So work and heat are not associated with the state of the system. What is associated with the system is the energy that you can get in the form of heat or work, both.
Okay. So thank you, sir, for answering the questions. I hope the questions are clear to the students who raised it. Okay, so with this, our webinar is over for the first half session. So we had a break from 1 to 2. So I request the participants to come just 10 minutes before the break and join in the webinar. So I would thank my speakers, Dr. Anupul Baru and Dr. Diganta Sharma, for their valuable time and giving such wonderful presentations to the undergraduate students. So we now I request our principal, sir, to say a few words for the session. Yes, sir.
Thank you both the speakers for cooperating with the students and delivering tonightly and presenting on this, their presentations. No doubt, initially we had some technical problems, and now they have been solved. Hope the next session will be now, Neha, you can go for next session.
Okay, so thank you all. We will meet in the next session starting at 2 p.m. Thank you all. So you can lead the meeting now.
Order.
Hello, am I audible? Hello.
Yes, ma'am.
Thank you. So, hello everyone. We are waiting for our speaker to come online. Then we'll start in a short while.
Okay, ma'am.
Please be patient.
Okay, ma'am.
Hello, am I audible? Hello.
Yes, ma'am, you are audible.
So, good afternoon. We are back with the second session of our webinar. So now our speaker is Dr. Rahul Kaur from Dibrugarh University. Let me give you a brief introduction of sir. So Dr. Rahul Kaur is currently an assistant professor at Dibrugarh University in the Department of Chemistry. And he has done his master's degree from Dibrugarh University, and then he moved for his PhD to Pune at National Chemical Laboratory. And he also has done postdoc in Japan, and currently he is guiding several PhD students, and his area of work is basically on theoretical chemistry based on DFT calculations. So with this introduction, I request Dr. Rahul Kaur sir to kindly present his work to our students. Thank you.
Yeah, thank you for the introduction.
Yeah,
Am I audible?
yes, sir.
Okay. So thank you for the introduction. And first, I would like to thank the Department of Chemistry, Dhemaji College, for extending an invitation to share something on quantum chemistry. I thought that the topic was too broad to be explained, but anyway, I accept the invitation and I thank all the faculty members, the head of the department, my students, and all the faculty members for extending the invitation. And I have, based on that invitation, I have prepared my presentation in a very basic kind of presentation, where I thought the main audience was or is the BSc students.
Yeah.
So please excuse me if it is too trivial for those who are expert in the subject. So this is my first apology. I thought I should say it before, and then I will start my presentation. So I have prepared my presentation in such a way that it is mostly for the BSc students and BSc major students mostly. So and the presentation is yeah. Is it fine?
Yeah.
Okay. So the presentation is basically quantum chemistry, and most of the BSc students know this subject, at least heard the name of the subject at some point of time. If not, then they will come across the subject. I mean, those who are first semester or third semester or second semester students, I think it is there in the fifth or sixth semester in the Dibrugarh University BSc course, major course. Although, as I said, that this is a very broad topic to be explained in 45 minutes or 1 hour. So what I thought is that I'll just give you some glimpse of what is quantum chemistry and how things are done in quantum chemistry and what one can get out of quantum chemistry. So for students, one may refer the books, Levine, McQuarrie, Atkins. These are very good standard books. One should read these books. Okay, so to start with, I will show some pictures, and I will be happy if any one of you can identify these pictures. 3, 4, 5, 6. Maybe some of you could identify some of the pictures and could relate them, but the names of these gentlemen are Planck,
Sir,
Heisenberg.
the pictures are not visible.
Pardon?
Sorry, sir, the pictures are not visible. The pictures are not visible.
The words are visible?
You are, yeah, the words are visible, but the pictures you are talking about, they are not visible.
Not visible.
No,
Then
sir.
it's the problem. This is visible?
No, sir.
What is visible? Can you just tell me?
It's the equation psi is equal to psi bracket q1, q3.
No. I thought I shared something else. Okay, just let me restart.
Okay, sir.
The window. Okay. Is it visible now?
Not yet, sir. It's loading. Yeah, it's visible. So can you make it in slideshow mode?
Yeah, I have
Yeah,
made it.
fine. Yeah, it's fine now.
Okay, great. So this is what I thought that I should show some pictures of the gentleman and motivate the students of by showing these pictures. So these are the pictures of Planck, Heisenberg, Schrödinger, Dirac, Pauli, Born. And I hope that students are smart enough to connect the pictures with the year is that they won the Nobel Prize in physics. And if you see the years, mostly in 1930s, 1940s, time where there was World War I, World War II. So there was kind of a pandemic situation and a crisis situation, the time we are facing just now due to the COVID-19 coronavirus case. So this was the situation that gave a lot of basic kind of, discovered a lot of basic kind of theories. So therefore, one has to get motivated by the situation rather than bogged down. So I have purposefully, I have not taken these picture. I mean, I chose the names randomly, and then there may be some names which I have missed. Basically, they were involved in the development of quantum mechanics. So as you know, that Planck was the first one who gave the equation of quantization, and then later on, Einstein, through the photoelectric effect, used the concept, and then he explained the photoelectric effect. And de Broglie was the another one who won the Nobel Prize, who also gave the duality particle wave dual behavior. And then Heisenberg, Schrödinger, and all those things, you know. So what about chemistry? Chemistry is, if you see these pictures, I think a few of you could identify them. So they were mostly involved in the development of or the use of quantum mechanics. Then they were mostly involved in the development of electronic structure theory. So they were Robert Mulliken, Hertzberg, Kohn, and Popel. So they were mostly in the late of 1960s, 70s, 80s. So they were the persons who were related in Nobel Prize in chemistry, and they related some electronic structure theories. And at this moment, I should also mention the name of Kenji Fuki and then Hoffman. So the question is that why do we need to study quantum chemistry? Basically, quantum chemistry is a subject which is developed based on the principles of quantum mechanics. And if one can say it in one line, it is basically solving the Schrödinger equation, that is H psi equals to E psi. So one has to solve the equation H psi equals to E psi, and then get informations about atomic and molecular systems. And these quantum mechanics was developed because of the failure of classical physics or classical mechanics. And in the 19th early 20th century, mostly the development of quantum mechanics started. So, fundamental understanding of atomic or molecular behavior one can get out of it. That is, one can understand a single molecule rather than 10 to the power 23 number of molecules. And then by application of quantum mechanics, one can do dry lab chemistry. That is what is known as computational quantum chemistry or computational chemistry in broad, and avoid wet lab chemistry. So wet lab chemistry is the chemistry where you do a lot of synthesis, you handle acids, bases, and all those things. So you avoid all those chemicals and you simply do chemistry with the help of a computer. So those are based on the principles of quantum mechanics. So what you can achieve almost all properties can be calculated or can be studied by using quantum chemistry. You can get the structures, you can get the spectra, IR spectra, NMR spectra, UV visible spectra, you can get the energetics, activation energies, kinetics, thermodynamics, enthalpy, free energy. You can even locate the transition state, which is rather very impossible to locate with experiments because of its short span. You can find out energy derivatives, properties like dipole moments, polarizability, hyperpolarizability, etc., etc. So that is why one should understand or one should read quantum chemistry so that one can apply it in understanding the properties using a computer. Initially, quantum chemistry model is simply some can understand. It is some system which is not real. It is some kind of a model system which replicates some real problem. For example, if I have a harmonic oscillator model system, linear harmonic oscillator model system, I can relate it to a bond, vibration of a bond, because vibration of a bond around the equilibrium distance is considered to be in harmonic motion. So I can mimic the harmonic oscillator model, the vibration of a bond. Similarly, rigid rotor can be used in understanding the rotation. So as we have already just said that these are built based on some postulates, based on some rules. So I'll not go into the rules, but I'll rather give you the flavor of the rules. The rules can be found in the book. Postulate 1 says something about wave function. What should be wave function? So wave function should be like this. So can you see the equation now?
Not yet, sir. Only the sentence is visible.
Only sentence is visible. Okay, I understood. So, okay. So postulate 1 says that you can say something about the wave function. Wave function means it is psi. So how is psi? Psi is basically now yeah, you have to bear with me because I'll change the windows. So this is psi. What is psi now? Psi is basically a function. Like f is a function of x. So psi is a function of some q1, q2, q3, and so on. And t, time. So what are q's? Q's are basically coordinates. X, y, z. So q1 is the coordinate, for example, if I take electron, so q1 is electronic coordinate for electron 1, q2 for electron 2, 3, and so on. And t is time. So basically all the informations that you want from a electronic system or atomic system or a molecular system can be found out from this wave function psi. Is it okay now? Can you see the slide?
No, sir, not yet.
Not yet? Okay. Yeah, this is the presentation. I think now you can see.
Yeah, it's loading. Yeah, it's visible now.
So this is where we were. And then the second postulate says something about the operators. So first postulate says about wave function. Second postulate says about operators. So what are operators? Operators are can you see?
Yes, sir.
Eigenfunction, eigenvalue?
Yeah.
Okay, so operators are basically some mathematical function. So here, let us say that A is the operator, which is some mathematical operator. It may be multiplication, it may be derivative, it may be integral, anything. So it's an operator. An operator is changes the function. So as you know, so if I operate A on any function psi, it changes psi, or it may give the same psi back. So here, it is the same psi back. So if I operate the psi with the operator A, I get some number A and then psi. So these kind of equations are called eigenvalue kind of equation. And psi is the eigenfunction, and A is the operator. And small a is your eigenvalue. So for example, if I take the operator as d2 by dx2 and psi as, say, it is 2x square, then one can operate psi as this. So you can get second derivative, and then you can take this. Finally, you get 4x, and then the answer is 4. Now, if you take another function, for example, psi is e to the power 2x. So if you take psi is e to the power 2x, then you see that the same operator, when it operates on the another function e to the power 2x, similarly, you get 4 e to the power 2x. So you can see that e to the power 2x is the same function you are getting back after you operate it with d2 dx2. Therefore, e to the power 2x is an eigenfunction. You're getting back the same function, and 4 is your eigenvalue. In the earlier case, it was not the same. Okay, so eigenfunction is e to the power 2x and eigenvalue is 4. Now there are another kind of operators, very important operators in quantum chemistry or mechanics, which are called Hermitian operators. Why Hermitian operators are important? Because Hermitian operators always give us real eigenvalues. Whatever we can observe, that observable can be always has to be an operator which are Hermitian operators. For example, energy. Hamiltonian is the corresponding operator, and therefore Hamiltonian is a Hermitian operator. So to every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. For example, observable is, say, energy. So the operator in quantum mechanics is your Hamiltonian operator. Okay. and they always give you real eigenvalues. Another important property of Hermitian operators is that eigenfunctions of Hermitian operators are always orthogonal to each other. And how do you define the Hermitian operators? You can find in any general textbook. It is defined in this way. Please note here that the first F star represents the complex conjugate of the function F. And the right hand side of the equation, it is A star. So I can define Hermitian operators from this definition. I can say that Hermitian operators are self-adjoint. Hermitian operators are self-adjoint. Another operators which are very important in quantum mechanics are commutator operators. Commutator operators are basically defined in the square bracket. If you have two operators A, B written in square bracket, I can write these as AB minus BA. Please note here that the operation is from the right to left of your screen. So in the right hand side, AB means B operates first and A operates after B. Minus BA means A operates first and after that B operates. And when we say a commutator operator A and B commute, means their result must be 0. That means AB kind of operation is equal to BA kind of operation. So then we say that operators A and B commute with each other. And if they commute with each other, there are very fundamental theorems in quantum mechanics which are very important. Say that if two operators commute, then they have same set of eigenfunctions. So the power of the theorem, you should appreciate that if two operators commute, then we can easily say that if I know the eigenfunction of any operator A, then I can straight away say that it is the same eigenfunction because of operator B, same eigenfunction of operator B because A and B commute with each other. The second important theorem about the commutator operator says that if two operators commute, then it is possible to find out a set of functions that are simultaneously eigenfunctions of both operators. So these two theorems are more or less very similar or related kind of theorems. And we know a very important commutator in quantum mechanics is that XPX is IH cross. XPX is IH cross. But XPY is 0 or YPX is 0. Okay? So only X and corresponding momentum operator in that X direction, they do not commute. Rather, all other commuters commute. They do not commute. That means they do not give 0, rather it is IH cross. But all others like X, PY, 0 or anything else is 0. Now coming back again to the equation. So we have first postulate says about wave functions, second about operators, third about observables. Observables means, for example, as I said, observable can be energy, it can be dipole, whatever you can observe, whatever properties you can calculate is your observable. So any observable can be calculated. For example, energy can be calculated simply as, pardon?
Sir, your presentation is not visible. Okay, it's loading now.
I think it should work.
Slide is there.
It should work. Is it okay?
No, it's not yet visible. Yeah, now it's visible. It's visible, sir, now.
Okay. So first postulate says about wave function, second says about operator, third says about observable, Observable means any property that you want to calculate. For example, if I want to calculate energy, I simply take the average of that. That means I simply take the average of that. So how do we represent that? Again, I have to change the thing. Why I have purposefully done this in 2-3 windows, because if students generally they see the equations, they run away. So I have so I thought that I should not show the equations first. Is it okay? Can you see a new slide?
It's
Some
loading,
equations?
sir. Yeah, now it's visible.
Okay. Just interrupt me if you have any problem. Okay.
Yes.
Okay. So observable of any operator, for example, here A is the operator. So its corresponding observable is given in this way, the average of A. So for example, if I want to calculate energy, the corresponding operator is Hamiltonian. Please remember that energy is the observable, operator is the Hamiltonian. So if I want to calculate energy of any system, I simply use this equation. Okay. So, and in the denominator, you can see that it's basically psi star psi d tau. So this is basically what we call as the normalization. I'll come to that point later. Now the question is that how to construct a Hamiltonian. If we want to find out the energy observable, and provided that we know what is the form of psi now, we don't know what is the form of H, Hamiltonian. So how do we construct a Hamiltonian? Or for any operator, for say. Let us discuss here only for the Hamiltonian. So Hamiltonian, what is Hamiltonian? If I take only in one dimension, Hamiltonian is basically the sum of kinetic energy and potential energy. So here we have considered only in the direction X. You can consider in Y, in Z, and you take simply sum. Okay, let us do only for X. So what is the classical representation of kinetic energy? In kinetic energy, it is px square by 2m. And the corresponding operator in quantum mechanics for momentum is h cross by I del del x. So this is what you have to remember, that the momentum, in momentum, the operator for the momentum is h cross by I del del x. Don't get confused by using the term h cross. Most of, some of you may have used h by 2 pi. H by 2 pi is equal to h cross. So it's h cross by I del del x. Partial derivative. So if you replace this now in the earlier classical representation of the kinetic energy, so that brings the kinetic energy operator. So you simply do the simple simplification, and then you find form which is minus h cross square by 2m d2 dx2. Okay. You could have written partial derivative also. Just I have written it because I just want to consider only one dimension. And operator for the potential energy is Vx. Again, Vx, you can ask the question that what will be the form of the potential energy operator for any given system. For example, if I consider any model system, it will depend on how the potential energy varies in that model system. For example, if I take harmonic oscillation model, in harmonic oscillation, we know that the potential energy varies parabolically. So the parabolic equation is some kx square kind of equation, kx square by 2 or half kx square. So potential energy varies as x square. So depends how you take what is the system. Okay. So again, so the Hamiltonian now can be written as sum of this Tx and Vx. Okay. So we know now this is the Hamiltonian of any system. If I want to write it for a 3-dimensional system, x, y, and z, the complete Hamiltonian H will simply be sum of this hx, hy, and hz. Please note that operators are always additive, hx plus hy plus hz. And wave functions are always product, not additive. Psi1 dot psi2 dot psi3, these are product functions, not additive. I cannot write psi1 plus psi2. Okay. So coming back again to the original, so this is the last one. I will not change now. Don't worry. So yeah, full screen mode. Chalo.
Yeah.
Yeah, is it okay?
Yes, sir.
Okay. So the fourth postulate says, interprets about the wave function. It says about the probability of finding the particle in some given space. First says about wave function. Second says about operator. Third says about how do we calculate the property. Fourth says about how we interpret the result. We know we get the wave function now. What is the interpretation? Interpretation is from the Born interpretation, who won the Nobel Prize for its statistical kind of interpretation. And then the fifth postulate is, again, is your postulate which separates out the time-dependent part and the time-independent part of the Schrodinger equation. I said that, so one, you will get now, if you do the mathematics, I have avoided the mathematics. If you do the mathematics, which is given there in this any standard book, you can find out that the Schrodinger equation can now be written as only as Schrodinger equation of time-independent part and time-dependent part. So we will discuss only for those systems which are time-independent kind of Schrodinger equation. And the very popular and a very fundamental model in quantum chemistry or quantum mechanics is the particle in a box problem. Why this is important, I'll come later. But let us first define what is a particle in a box, or free particle in a box. So if you have any particle, it may be electron or any subatomic particle. So for example, if you have an electron which is free to move in any direction, for example, say x direction or y direction, z direction. So we are taking it in one dimension, so it is allowed to move only in, say, for example, x direction. So let us construct a box with the walls. And your particle is allowed to move in this x direction, either positive x or negative x, whatever. Okay? And we define the box, walls of the box in such a way that it has a potential of infinite potential. That means the particle cannot cross the barrier, cannot come out of the box. The particle is always inside the box. It is free to move inside the box, but it cannot come out of the box because now we have defined the potential walls as infinite potentials. And as it is free to move inside the box, so the potential energy is considered to be constant and assumed to be zero. Now, we define the box in such a way that one of the box is in 0 coordinate, walls is in 0, and another wall is in some separation L. So the separation between two walls is L. One is at 0, another is at L. So separation of two walls is L. So again, from our knowledge of the Hamiltonian operator, we can write that the Hamiltonian operator in one dimension can be simply written as kinetic energy operator, that is minus h cross square by 2m d2 dx2 plus vx, potential energy. And we know that in this problem, potential energy is 0. Okay? So we'll use that. But what is the Schrodinger equation that we have to solve? We have to solve that h psi equals to E psi. We have to find out what will be the psi of that free particle which is moving inside the box. What are the possible energies of the free particle that is moving inside the box? So what is h psi? You replace h operator and operate it on any psi, general psi, and which is equal to E psi. So now, Vx is 0. So left hand side becomes only h cross square by twice m d2 psi dx e psi. So if you rearrange this equation, this is basically some kind of a second order differential equation, which the chemistry students who have mathematics can easily relate this equation to the second order differential equation. And its solutions are not that difficult. The solutions of this differential equation is a standard solution, and it has some a cos kx, b sin kx. Okay, I have not written in terms of exponential, I have directly written in terms of cos kx plus b sin kx. So here we have introduced two terms. One is a, another b, which are constant terms, and another term which is k. Okay. Now, what is k? K is basically 2me. M is the mass of the particle, E is the energy, and h cross. Okay. So this is what is k. Now, if you take the same definition of the box, now inside the box, the particle has some function psi x. Because particle cannot go outside the box, the wave function outside the box is 0. Okay, psi 0, 0 and psi L 0. Now, in order to get a meaningful expression for this energy and psi, we have to consider the boundary condition. What is boundary condition? Boundary condition is the condition which is defined at the boundary. What is the boundary in this case? Boundary is your walls, which is placed at 0 and at L. So what happens at 0? At 0, x equals to 0, we have psi equals to 0, because particle cannot come out of the box. So psi will be 0 at x equal to 0. If psi is 0 at x equals to 0, and if I put this in our earlier expression a cos b sin x, we can straight away say that a equals to 0. If my psi is 0, that means my left hand side of the equation is 0. That means cos of kx plus b sin of kx. From that equation, b k sin of 0 is not 0. So first term a must be 0. On the other hand, if you take x equal to L, same. At x equal to L, the particle cannot cross the barrier, and therefore it is not found outside the box. And therefore your psi L, which is now defined as, because a is 0, there will be no cos term, only sin term. So b sin k L. Now x is L. Is 0. So this is the condition which is only satisfied by not considering b. I'm sorry. If you consider b equals to 0, that means that your whole equation psi is 0 everywhere, which is not possible. We want psi inside the box. Outside the box, it is 0. But if we put b equals to 0, a is also 0, the whole psi becomes 0. That is what we don't want. So therefore, b cannot be 0. So if b cannot be 0, what is the other possibility which satisfies this condition? The condition is that KL must be equal to n pi. KL must be equal to n pi, because psi, if I take n equals to 1, 2, 3, if I take n equals to 1, that means sin pi is 0. n2 again, n3 again. So only in that condition this equation is satisfied. So we know that KL has some integral value of some pi. Now the question is, why n cannot be 0? If you take n equals to 0, again, if you take n equals to 0, your psi becomes 0, which means that particle is nowhere. Psi is 0 even inside the box, and particle is nowhere, which is not true. So n cannot be 0. Now if you do some simple modifications of this equation, K equals to this, and you replace the K value as n pi by L, because KL equals to n pi. So n pi by L, and you rearrange a little bit, you get an equation which is the equation or the energy of the particle inside the box, where I have used a subscript n to represent that E1, n value 1, E1 will be different, n value 2, E2 will be different, okay? And this energy varies quadratically. Quadratically, why quadratically? Because it depends n square kind of thing. It's not linear kind of variation, it's quadratic kind of variation. So it's n square kind of dependence. So you have n equals to 1, 2, 3, you get different values of energy. So these are the two important things that I have highlighted. Now, what is the form of the wave function? Wave function, to find out the form of the wave function, we have to again go back to the equation. That is B sine kx, and consider the condition that k equals to KL equals to n pi. Okay? And replace the value in place of k. So if you replace the value, your psi n x equals to B sine n pi by x. Now the task remains is that what is the value of B? So here comes the Born interpretation. That probability that the particle lies between the boundaries 0 to L, that means inside the box, must be given by this expression. That means you have to multiply psi star psi, which is the probability density, and to multiply that with the volume element dx, small volume element. If you assume that the box of length L can be made small boxes of length dl, 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 and then you take the probability of that psi star psi in dl1, psi star psi dl2, and then you go on and add from 0 of the box to L of the box. So this is the representation of this. This is the physical meaning of this equation. That means you sum over all such probability density of the volume element of particle, of finding the particle. So normalize that condition. So this value must be equal to 1. So if you use that condition for this wave function and replace psi n by B psi n pi x by L in this equation, we get the value of B equals to, you have to do some simple integration, and you can find the value which is given in any standard books. You can find out the value of B comes out as 2 by L to the power half. Now if you put the value in the wave function, your wave function becomes 2 by L sine this. So this is your complete wave function. So we have solved the Schrodinger equation. We have solved the Schrodinger equation. We have solved means we have got the energy values, we have got the wave functions for the particle inside the one-dimensional box. Now let us see what are the physical interpretation or physical meaning can we get out from the box. So energy is n square, dependence wave function is this. So now again, if I plot a box, okay, this box is too big, but you will understand why it is too big now. So the box is defined 0 to L. I have taken again in x direction. Same thing I am doing repeatedly. Energy increases in this direction, and for n equals to 1, if you replace in energy E1 subscript 1, E1 equals to h square by 8 pi n. So left hand side value represents the energy for the value n equals to 1. So the energy for this is some value given by the blue line. And this is the energy corresponding to n equals to 1. Now, what is the wave function corresponding to n equals to 1? Please note that this wave function varies as sine function. So the shape of the wave function will be like sinusoidal function. So n equals to 1, it has this. If I take, this is psi 1. So if I take n equals to 2, energy is 4h square by 8 pi n, pi 8 ml square, and your energy, your wave function is now this. Outside it is not, there is no wave function, only inside it is there, because outside psi is 0. Inside it is psi 2, is psi 2. Then for n equals to 3, you can put the values easily. And you see that the gap, it was h, it was 4, it is 9. So the gap will also increase between consecutive levels. So the wave function is this. So this is psi 3, psi 4. So this is the wave function. You can see that these are sinusoidal kind of wave functions, sine functions, because your wave function psi x is some constant into sine and pi x. So you know, you can see that at some value of x, at some value of x, your wave function is 0. That means it is, if you see n equals to 2, from left of your screen to right of your screen, it starts, crosses the blue line, goes down, and again comes up. So this crossing at this point is what is called as a node, N-O-D-E, node. So node represents a point where psi equal to 0. So you can find the point at which psi becomes equal to 0. You can see that for n equals to 1, there is one node. N equals to 1, there is no node. N equals to 2, 1, 3, 2, 4, 3. So there are n minus 1 number of nodes that are present in psi. Now, if I take the probability density, that means psi square, what will be the plot? The plots will be like this. These are not very exact kind of plots. Just I have tried to make it myself. Please excuse me. These are not looking similar to that in the book. You can refer the book for exact plots, but just to get the flavor that these are the plots. So psi square is again some sine square kind of function. So sine square will be like this. So it will not become like this. Okay. So these are sine square kind of functions. So if you know how sine square behaves, you can plot. If you put the value of any value of n, you can find out the probability density and plot the probability density. Here, please note that here they are not crossing 0. So here you don't get any node. Representation of node is only from this psi, not from psi square kind of. Now again, if I take the box, same box, and I write the energy as n square h square for any value of n. It may be 1, 2, 3, any value. The energy will be, say, for example, I have this. Now, if I take a consecutive energy level, say n plus 1, next energy level, okay, consecutive energy level, I'm increasing it. Okay. So you replace value of n with n plus 1, the equation remains same. Simply replace it with n plus 1. You get an energy which is n plus 1. Now, if you have an electron or a particle in n, then you can make a transition from n to n plus 1. So you can make a transition from n to n plus 1. So you can see here. So you can make a transition. What does this mean? That if we can find out the energy difference between these two levels, any n plus 1 and any n, the energy difference is del E, which is basically the difference of the above two equations. and which comes out simply as 2n plus 1 h square by 8n square. So if you know the separation between any two energy levels, you can find out the frequency or any other related properties, if you consider the system to be a particle in a one-dimensional box. Another important thing, that now if your box length of the box is increased, if I increase the length of the box from 0 to L to say 2L or 3L or 4L, I'm increasing the box, length of the box. So 2L, 3L, 4L. What happens? See the expression. Denominator, it increases. That means my del E becomes smaller. Denominator increases, means my del E becomes smaller and smaller if I go on increasing the box. So that means if I go on increasing the box, the quantization which I get, what is quantization? Quantization is the discreteness. Discreteness of these energy levels. For n equals to, for example, n equals to 1, I get some energy. For n equals to 2, I get some another energy. N equals to 3, there is another energy, which are not continuous, which are discrete, which are separated out. So this discreteness, this quantization of energy levels is lost when you make the box larger and larger. That means if you think of a particle as a really free particle which can move, which don't have any boundary, I have extended the box in such a way that there is no boundary, as if there is no boundary. That means there is no quantization. The particle is free to move. One can say that this quantization of energy comes from the fact that there is a boundary. If there is no boundary, there is no quantization. Okay. Again, if mass increases, that means again there is no quantization, because generally we talk of subatomic particles, okay, which has very small mass. So that is why this equation is very important. Now, if we extend this to a three-dimensional box, we have one dimension in X. Just imagine that you have another dimension in Y, another dimension in Z. And I bring the three dimensions in one axis, X, Y, Z. So I get this box. It is, say, a rectangular box. It may be kind of any rectangular shaped box, okay? Any box which has, say, in x-axis, it has a length Lx. Like earlier, the length of the box was L, 0 to L. Here, the length of the box is 0 to Lx, or length of the box is Lx, Ly, Lz. Okay, these are the three lengths in 3 dimensions. Again, the particle inside the box has potential energy 0. Outside the box, the particle walls are so big that it has infinite, cannot come out of the box. So if I extend the methodology similarly, here the definition is very important, that the particle potential energy is 0 in the range where x 0 to Lx. Earlier we took only 0 to x, 0 to L. Here we are taking three directions, x, y, z. So we are defining Lx, Ly, Lz. Since the probability for the particle to have infinite energy is 0, the wave function must be 0 inside the box. Outside the box, sorry, outside the box, because you cannot find the particle outside the box. So again, if I use the Hamiltonian for 3 dimension, the first term in the square bracket, if you neglect the last 2 terms of the first bracket, that represents the Hamiltonian in 1 dimension. Now, if you take 2 terms, this is the Hamiltonian in 3 dimension. So therefore, you have this is the Schrodinger equation in 3 dimension. You have not taken potential energy because Vx, y, z is 0. And as I said that if now we consider that our wave function is a product function, Hamiltonian is the sum of Hamiltonian. there's a very important theorem that comes here, is that if you can write wave function as product function, operator as sum of operators, then your energy value or the eigenvalues can also be written as the sum of eigenvalues. Okay, so this is a very important point. So what is the eigenvalue? Eigenvalue is the energy, which now depends on three numbers: nx, ny, nz. Because now you have to appreciate that nx can have different values, ny can have different values than nx, nz. Nz can again have different values than nx and ny. So as I said, that if you can write the operator as sum of operators, then you can write the energy values as sum of energies. Okay, so this is why we have made this derivation very short. This is the power of that. And what is x? X is the wave function in x direction. The same. Just you have to be careful that you are using Lx and sine n pi x, because you are considering only in x direction. For y and z, it is again, you have to be careful in using y and z functions. Now, a very important point here is that a condition which arises, that if for some reason all the lengths Lx, Ly, Lz are same, that means that we have a cubic box. In a cubic box, all the edges are same length. So in that case, what will be the energy? Energy will have L square. Okay, it becomes even simpler now. So it's nx square, ny square, Lz. This energy is only valid for a cubic box. Okay, for any general rectangular box or any other box, this is not the energy. The earlier one is the energy. Now again, if you take now, like earlier, nx, ny, nz can have values 1, 2, 3, and so on. They cannot have 0. Okay. So what are the possibilities of the energy? Now the possibilities of the energies will depend on what are the values of nx square, ny square, nz square. So let us plot these possibilities with the energy. Now, what is the lowest possibility that nx, ny, nz can have? Each of these can have the lowest value, that is nx can be 1, ny can be 1, nz can be 1. So in that case, it is 3. nx, ny, nx square, ny square plus nz square is 3. So you get an energy level corresponding to this. So what is the wave function for that? Wave function will be psi 1, 1, 1. What is psi 1, 1? Psi 1, 1 is nx value has 1, ny value has 1, and z value has 1. So you get an state. I say wave function is a state. You get a state for an energy corresponding to this. Only one state. There are no other possibilities. Okay, so we call these as non-degenerate state. Next, what is the possibility? It can have 6. The values can be either 2, 1, 1. So nx can have 2, ny can have 1, nz can have 1. Similarly, in this case, it may be either nx1, ny2, nz1, or nx1, ny1, nz2. All these three will have same energy. All these three will have same energy, but their wave functions will be different. One will have psi 2, 1, 1, another will have psi 1, 2, 1, another will have psi 1, 1, 2. So all these three will have different wave functions, different states representing same energy. Because they are representing different states but same energy, these states are called degenerate states. The earlier one was non-degenerate, now these are degenerate. So degenerate state means if you have anything 2 or more than 2 states which have same energy, then those states are called degenerate states. If I go on, 9 is this, 11 again triply degenerate. 12 is singly degenerate or non-degenerate. You can go on as an exercise. If you want, you can try different values of nx, ny, and nz and try to find out what are the different states. Now the next point that comes here is that stationary state wave functions. Stationary states are the states. Very simply, if I say stationary states are the states which are time independent states, which do not have the time dependent part. Okay, that means probability density is time independent. So here, for example, if I take psi 211, psi 121, psi 112, these are all stationary states. All these are stationary states. Okay, and if you consider only these three stationary states, psi 211, psi 121, psi 112, for the particle box are degenerate. Okay. Now I will stop my presentation with the question that will a linear combination of these three degenerate stationary state wave functions, that means C1 psi 211 plus C2 psi 1 plus C3 psi 112. So this is a linear combination. So will a linear combination be an eigenfunction of the particle in a cubic box Hamiltonian? So this is the question I pose and I stop my presentation. So if you have any question, you can ask. Thank you very much for listening.
Thank you, sir, for your presentation, for introducing the basics of quantum chemistry to the.
Yeah. So
Hello?
did I take my time was okay? I think okay.
Yeah. So thank you for your wonderful presentation, for introducing the basics of quantum chemistry to the undergraduate students. So we have two questions. So
Yes.
first, what is the physical significance of commutation of operators? What is the physical significance of commutation of operators?
Okay. What is the other question?
Other question is, what are the acceptability conditions of wave functions?
Okay. So first question, physical significance is that if you, as I said, if two operators, if you say A and B, if they commute, that means that one can, that means if you operate AB or BA, you are, the physical significance is that, I can say in this way that if you operate AB or you operate BA, you get the same value. And important point to be noted is that the eigenfunctions of these, if they commute, the eigenfunctions of these two commutator operators are same. And the second question is, what are the acceptability conditions are, I think is there in the book. You can find out that psi must be well behaved. To be well behaved, psi must have single valued. That means for each value of x, psi must have one value of x. It cannot have two value of x. There must be a continuity of psi. There cannot be discontinuous psi. Functions cannot be discontinuous functions. I think, yes. Maybe some other, I forgot. I don't know. Maybe these are there in the books. It's not a big issue. But important point is that the psi must be to well behaved. It must have a single value, and it must be continuous function. And its derivative must also be continuous function. If I have answered it to the satisfaction, or if someone wants to ask anything more.
Yes, sir. We have one more question from the student. The question is, can the quantum wave function of entangled systems be objects that exist in normal three-dimensional space?
Can you repeat the question?
Yeah. Can the quantum wave functions of entangled system be objects that exist in normal three-dimensional space?
Entangled systems.
Yeah.
What kind of systems he is talking about?
Mr. Pradeep Saikia, can you please unmute yourself and clarify your question? Mr. Pradeep Saikia? Sorry, sir, I think he's not responding. Pradeep Saikia, can you hear me? Pradeep Saikia? No, sir, there is no response.
Okay.
Okay, so then we can avoid this question. So thank you, sir, for giving us your valuable time. Okay, thank
Thank you.
you.
Thank you very much. Thank you. So I can leave.
Yes, sir.
Okay. Thank you.
So our next speaker is Dr. Ankur Kanti Guha. So Ankur sir has not joined us yet because of some network issues. Let's wait for a few minutes. Please don't be impatient because you know there are network issues going on. Just give us a few minutes. If he's online, we will give you his brief introduction and then proceed on with his talk. Okay, so I request all of you to wait for 5 minutes. Dr. Ankur Kanti Guha is facing some network issues. He's trying to resolve it. Just give us 5 minutes. We'll be back. Please do not leave the meeting, okay?
Okay, ma'am.
Okay. We are sorry, we are just waiting till 3:30. If sir is not able to join us, then we will proceed with the concluding part of the webinar. I'm audible, right? Hello?
Yes, yes, ma'am, you are audible.
Okay, okay, thank you. Okay, so Ankur Kanti Guha sir has joined us. We are really very sorry for the delay because network issues can't be avoided. So now let me give you an introduction of our next speaker, who is Dr. Ankur Kanti Guha, and he is currently an assistant professor at Cotton College State University, and he did his masters from Guwahati University. His PhD is from Tezpur University. After his PhD, he also did a postdoc at Indian Institute of Technology, Kanpur, that is IIT Kanpur, and he's currently working on theoretical chemistry. That means his research is basic on theoretical chemistry based. So I would request Ankur Kanti Guha sir to kindly present his talk. So sorry participants, we have to cancel the talk of Dr. Ankur Kanti Guha because he has not been able to resolve the issue and we can't keep on you waiting. So now we are heading towards the end of the webinar, and a webinar or seminar is always marked by a vote of thanks. So now I'll be presenting the vote of thanks, and also will let you know the updates about the certificates for the participants. So I'm extremely thankful to all who supported us in making this webinar a success. I know there has been some technological issues, but since the situations are such, because we have never organized a seminar online and this is our first time, so next time we'll try to resolve these issues so that the participants don't suffer, but still I hope you will pardon us. And I would also like to express my gratitude to our principal sir, Dr. Deepak Kumar Miyok, for his encouraging speech in the morning session and also inaugurating the webinar. I also thank the IQAC cell of Dhimaji College for their support. I would like to thank our HOD sir, Dipen Kaputi, for his speech and moral support and guidance he has given to all his department colleagues. I also would like to acknowledge my thanks to Dr. Manas Pratim Bolwa and also to our convener, Dr. Manas Pratim Borpujari, because he has single-handedly managed all the issues of the seminar. All the arrangements were made by him. So I, on behalf of all the participants, also thank him. Then I express my sincere thanks to our speakers, Dr. Diganto Sharma, Dr. Anupul Bolwa, Dr. Rahul Kaur, and also thankful to Dr. Ankur Kanti Guha because he was willing to give the participant, but network issues did not permit. And the rest of the speakers have given wonderful talks to the students, and I hope you enjoyed the presentations during this lockdown period. And finally, I thank all the wonderful students who are our main audience, and you have turned up in such great numbers. And the interesting thing to note is that we have participants not only from our college, from all over Assam, from different colleges, and also from different parts of the country. I can see some students from Delhi, from Uttar Pradesh, from Haryana. It's great to see students turn up in such great numbers because it encourages us that our efforts are being successful, because this webinar is organized for the undergraduate students. And once again, I thank all for your cordial cooperation in making the webinar Interdisciplinary Topics in Chemistry for the Budding Chemist a success. And let's hope that the world gets coronavirus free soon and we can be back to our normal lives where we can physically interact with each other in the seminar. And so now that marks the end of the webinar. And regarding the certificates, the participants who have attended the webinar via Google Meet or YouTube Live, whoever have left comments in the comment section below, the certificates will be sent to your respective email IDs. But please be patient because everything will be the certificate will be e-version, right? We won't be sending any hard copy. So it might take some time. By end of June, the certificates will be sent in your respective email IDs. So with this, I end the webinar. Thank you all. So now you can leave the webinar. Thank you.